Hello.
Hello, Prof. Chen Gao.
Yeah, you can hear me.
How are
Yeah.
you?
Hello, Cecile. Yeah, I'm fine.
Nice.
Good.
So you also moved to the new office?
Yeah. In June this year, we moved to Mohot. Yeah.
Yeah. And the offices at Mohot are better than at Marine Technology Center.
So far, so good.
It's better.
Yeah. It's more like a teaching setting.
Yeah.
Yeah.
Hi,
So it's not very good for labs.
Hi.
Hello,
Hi.
Prof.
Hi,
Davik.
Hello. Hello.
Prof. Yanjun.
Professor Fu.
Hello.
Yeah. Hello, Professor Mon. Yeah. Professor
Hello.
Gao. Yeah.
Hi.
I suggest everyone, if possible, you can start your webcam so that we can see each other.
Wang Ling, you didn't open your camera. We didn't see you.
Yes, I'm in the office of the meeting room of Ningbo Oriental Cable, and later they will start the camera.
Okay.
Yeah, all together. Yeah.
Okay, now you can see us, I think.
Nice. Yeah.
I'm together with Mr. Shilu Hao.
Good. You look like a professional now.
Yeah.
Thank you, thank you.
Like a general manager, right? CEO. Shilu Hao, he was master of NTU. Do you know him?
Dr. Fu, yeah.
Yeah, I mean, Pokemon Swin. He graduated from NTU at 2017. No, 18, right?
Yeah, I start from 2017 and graduate from 19. Yeah, I've been talk to Moon like this. Yeah.
At that time, he
Yes.
was in fish farming structures, supervised by Paul Rudder and me. So
Yeah.
Mm.
Okay. Prof. Mon, I think now it's time to start. It's 2:30.
Yeah. Do you allow me to share the screen?
Yes. Can you share the screen now?
I will try. It seems okay. Yes.
Okay.
okay, we can see it clearly.
Can we see the full screen mode?
Right.
Noen som får til kamera?
Okay.
It's ready?
Yes.
Yes.
It's clear.
Okay. So good afternoon in China.
Yes, good afternoon.
Good morning in Norway. To say good night in USA.
Oh, who is in USA?
I am face to face, but I hope that we can do so soon. I wish everyone welcome to this workshop under the auspices of the NBO Academician Workstation.
你这个
And
你
the work
是做的这个抗菌剂吗？还是做的树脂啊？树脂的啊，树脂做抑菌，反正我估计效果不会太好。
Who was talking?
Please keep yourself muted.
它是啥呢？一般是它那个小分子嘛，小分子比如说渗透到你边上的那个虫子里面嘛，剖开来，然后再把这个虫子里面这个细菌杀死，它形成一个透明圈。如果你是一个树脂，是一个大分子的话，你有活跃光，也有什么东西，它不容易出去嘛，所以你这个做抑菌反正效果可能不会太好。你要做的话，最好是，但是你做一下也可以，你就看一下它这 这个贴在树脂这个下面啊，下面
你们把它踢出去可以了，踢出去。
如果不长的
We
话，
should
你这
mute
个
him.
就要跳，对吧？那你把这个贴在上面，对吧？接下来再下
踢
这一块才是你真正接触的地方。所以最准的办法是，实际上就是像我们做的这种。
Was some problem, I think. So Prof. Mon, maybe you can continue. We cannot hear you.
Yes. Okay, you can start. You were muted. Okay, also. You remove your mute. Okay. You were muted.
Prof. Mon, I think you can unmute yourself.
Okay, you were muted. Okay. Your left down side. Left down side.
Yeah.
No,
I lost.
okay. We can hear you. Okay.
You hear me now?
Yes, now okay.
Now, yes,
I-
back to normal.
Okay, so welcome again, everyone. And here you see the tight focus on power cables for floating wind turbines. And it is organized by Ningbo Orient Cable, Ningbo University, NTNU, and SINTEF. Let me say a few words about the academician workstation first. The host is Ningbo Orient Cable PTL Limited. And the key partners are NBO, Ningbo University, NTNU, and SINTEF. And we will encourage cooperation, of course, with other organizations not being a so-called key partner from the beginning. And aim and scope of this academician workstation in the short-term perspective, design, loadout, installation, and operation of electric power cable systems. We also, in the more long-term perspective, would like to include innovative wind turbines and substation design as illustrated in this slide. The background for the academician workstation, and so to say also this workshop, is that wind together with solar power is expected to be the dominant renewable energy source in the global energy mix. In 2030 and 2050, renewables are forecasted to make up about 30 and more than 60% respectively of the global energy supply. But this slide focuses on wind energy, and plot shows the installed wind power up to December last year, and the total is about 850 gigawatt, and is dominated by onshore wind energy. The offshore contribution was about 50 gigawatt, as illustrated in the plot below to the left. And but as you can see here, gigawatt installed offshore by now, it is expected to more than 3 times in the next 5 years, 27. And these are forecasts which are fairly accurate because they are mainly on confirmed projects. So the contribution then from floating wind energy is still quite modest. It's about 0.1 gigawatt today, but is also expected to grow significantly the next 5 years, as indicated here. So it's expected to be about what installed in 5 years' time. And you see that are very steep. The growth is very big. And also regarding the development of the forecasts are pretty accurate because they are based on confirmed projects, essentially. Any engineered system or facility experience a life cycle consisting of design, fabrication, installation, as well as operation. The design is particularly important. The design is supported by analysis, and it is supposed to demonstrate compliance with serviceability and safety requirements that reflect loads imposed during installation, and especially during, as indicated to the left here. In this connection, design standards play an important role. Standards for floating wind turbines and dynamic power cables are gradually emerging. Acceptable serviceability and safety are primarily ensured by design, but in addition, quality assurance and control by inspection during fabrication and inspection and monitoring during operation is also crucial. On this background, the aim of the present workshop is to share knowledge and ideas regarding using the opportunities of power cables in the industry, as well as addressing challenges, partly due to new features of cables for floating wind turbines. And this will be done in view of the state of art of power cables, operational experiences, and previous and ongoing research and development. So then we should be ready to start the presentation. So I would like to hand over the screen to Professor Van Ling of Ningbo University. He will chair the following sessions. Let us hope for a constructive and interesting workshop. Thank you.
Thank you for an excellent introduction. Then good morning and good afternoon, everyone. I'm Ling Wan from Ningbo University, and I will be the host for this upcoming international workshop. Okay. Before the next presentation, I would like to highlight some information. Okay. This meeting is recorded, and if you have objections, please let me know. So we will keep the part confidential. And for information, there are two platforms synchronizing here. We have Zoom and Weijian. So in Weijian, when you have questions, you may key in your questions in the chat box. In total, there are 10 presentations in this workshop. They are divided into 2 sessions with a coffee break in between. And after each presentation, there will be 5 minutes for Q&A sessions. Then in these 5 minutes, we can have about 1 or 2 questions. Okay. So when the speaker is presenting, please keep yourself muted. Okay. So then let's welcome Professor Sven Sævik from NTNU to give a presentation. Prof. Sævik got his master and PhD degrees from NTNU, and he has many years of experience as chief engineer at Rinerton Engineering and also as chief scientist at Sintef Ocean. Since 2009, Sven Savik became the professor in Department of Marine Technology at NTNU. More importantly, Prof. Savik is a developer of widely used software for power cables, umbilicals, and flexible risers. Okay, Prof. Savik, I would like to hand over to you to give your presentation. Thank you.
Thank you for a very nice introduction. I shall try and share my screen. Let's see whether I succeed with that. First of all,
Mon,
can
I think
everyone
you
hear
should
me?
stop your sharing first. Prof. Mon, you should stop your sharing first. Yeah.
Okay. Can everyone see my screen?
Yes, we can see
Okay.
very clearly.
Okay. Then I would like to give this presentation, which I've entitled "Overview and Knowledge Gaps in the Program." And of course, it's related to power cable strength issues, which is have been the focus in my work that relates to this. So I shall have some introductory remarks. I shall talk a little bit about loads and failure modes that relates to load out, installation and operation. Some comments are given regarding works that have been done or are ongoing to close some of the gaps that I'm going to mention. I will also comment on, because we don't only have the dynamic, we also have a static section, so I will give which is in some context also have some dynamic things into it. So I will just comment briefly on that also, and then I have an example calculation on the role of different responses that relates to a dynamic power cable risers before jumping into some concluding remarks. As you know, the power cables in the offshore industry have different applications where the primary focus in this presentation is related to the application of wind turbines, where that includes both alternating current cables and direct current cables, and which also then in the floating wind turbine case, you will have to use a dynamic cable that connects the floating infrastructure to the seabed. And it's to be noted that the dynamic cables are normally, but not necessarily, double armored to ensure a torsion balance. That is, I think it's fair to have in mind when I'm talking about this. This is a kind of attempt to see the typical scenario that we face. We're having this green dynamic riser section, which is normally an alternating current cable, and the inter-array, which is then collecting together these different dynamic AC cables into a bigger one, and then to the substation, which then transform it into DC and the export cable, depending on the distance to the infrastructure on shore, will normally be a DC cable to avoid energy loss. So this AC is a typically three-phased cable, and this DC is typically having a core and some screening on the outside. So they are quite different in structure, if you look from the cross-sectional structure point of view. Okay, so then if you now look at the installation scenario, where you are having an installation vessel and you install the cable, then of course it will be exposed to current waves and vessel motions and horizontal loads that will give you global responses that will cause tension and torque variation. It depends a little bit on the heading of the vessel and yaw and so on. Of course, the water depth is if you're talking about torque, then the water depth is a primary variable, because total yaw motion versus the water depth gives the torque into the catenary. It will cause curvature variations, and at the contact point with the seabed, you might have compression, which is basically a limiting criteria as of today with regard to how much, what is the weather window you have to install this power cable, because the state of the art is to try to avoid this compression, because you are the bending stiffness is very low, and you can very easily, if you combine torque, even if you have tension, you can go into kink and Hockling formation, which means a corkscrew, and that is an irreversible process. There's no way back if you have got this, because you have inherent friction. So if you try to straighten out, you will simply damage the product. Then I mentioned some knowledge gaps from my point of view. That is the accurate constitutive models in order to perform accurate global analysis with the proper link between torsion and curvature. And also that is because this power cables, in order to avoid corrosion in the armor, you normally either you can use galvanized wires or you embed them in some bitumen, and this bitumen is very temperature sensitive, and of course then gives a stiffness or bending stiffness that is very much varying on the temperature. So that is a very uncertain factor with respect to both the installation and the operation of this cable. Then you can then have interaction with local failures on each component level. Each wire can go into lateral buckling, or you can have bird caging, and I would say that I have said this many times, that there's a need to have validation by experimental and numerical procedures. So what I put into that is that this moment curvature behavior should be a topic of standard validations test for each project, in my opinion, because it is very sensitive to manufacturing issues like the shrinking of the outer sheet following the extrusion and so on, or if you have the outer sheet or not, that will totally change the moment curvature behavior. Loadout is also a very important part. We have seen failures, and we have had some ongoing activities that relate to this, where you are transporting the product from the factory to the spool on the vessel prior to the installation, or also, of course, parts of the loadout procedure from the vessel. And the thing is that depending on certain parameters like viscoelastic effects in the outer sheet, if it is an outer sheet, for any change in the curvature plane, you would introduce cork, and that can be a kind of an exponential process. So you build in it getting stiffer and stiffer, and you are getting more and more torque until the compressive stresses in one layer is so big that you're getting either bird caging or some forms of lateral buckling. And that is, so I would say that there are certainly knowledge gaps that related to the constitutive models, as was already mentioned, but also algorithms or models that allows you to investigate what is favorable with respect to the root geometry design, depending on what kind of cross-section you have in hand. Of course, the bitumen is also playing a role here. If you are loading up at low temperature, you will have very high friction moment, and will certainly influence what you can do or not on the loadout procedure. And of course, you have to have, in order to put up the correct, say yes or no to this loadout procedure, you need to have good grip on the local failure modes. And I will again point out the need for validation testing in order to be sure that you can actually do this. Then we're over to the operational phase. We have now connected the dynamic racer to the platform, and we are exposing it to dynamic loads. And these dynamic loads, in terms of moment and curvature and tension, are now transported into local stresses into each wire of the cross section. And we normally have this bending stiffener in order to limit the curvature at the top connection point, which we normally consider as the most critical one. But it might not necessarily be so, depending on what kind of configuration you have in hand. Then you are having horizontal forces, as you will have during installation. But you can also have contribution from vortex-induced vibrations, and that vortex-induced vibration might be introduced from current waves, and also floater motions whenever you have a relative velocity between the riser and the water. And of course, this will give you tension and curvature variation and leading to local bending and friction between the wires, causing cyclic stress variations that can introduce cracks and fatigue in the different components. That includes the tensile armor and the copper conductor and the screenings, which also might be quite, depending on how this is designed, can be quite a fragile thing. Again, there's a need to the same things that I have already mentioned. This is constitutive models, moment curvature, coupling between torsion and curvature, depending on what type of torsion you have in hand, and the need for validating this with respect to experimental procedures and to validate the numerical models. Then, in addition, you have thermomechanic coupling effects due to variation in temperature. So you're having something which is hanging down, and you are having gravity forces. You're having temperature variations due to the power production from the wind turbine, which you might have to stop, and then it will cool down. You have some coupling effects that might have an influence on the total fatigue life. And of course, there's a need that has been a kind of a thing in ocean engineering for many years to have a model that are able to combine the Morrison load effects with the VIV load effects so that you're having one consistent calculation. This is kind of the standard procedure in order to validate the fatigue life. You are doing some global analysis, you're transforming that into local stresses, and you're using the histogram of stress ranges and combine that with the fatigue data in terms of SN diagram for each component. That is kind of the standard procedure. If you look at the state of the art, global analysis by Morrison load effects, they are provided by several commercial computer programs, as you know. That is, but when it comes to the combination of VIV and also this, first of all, these Morrison loads, they are done in the time domain because these tools, they are providing time domain analysis. But when it comes to the VIV, the state of the art also as of today, that is to use frequency domain tools like Share7 and Viva or Vivana, where you simply take the results from the frequency domain VIV response analysis and add it to what the fatigue damage that we have in the Morrison one, which of course is not a consistent procedure, because to be consistent, you should have everything in the same stress signal. So you should have one stress as a function of time containing all these load contributions into the same stress. When it comes to local responses, to convert a global response into time series of stress, there's many different tools, and I have been involved in developing several of them, like the Sinterforsen software Pflex, Uflex, and USAP. And of course, general tools like Abacus and ANSYS can be used for this purpose. And that's to be noted is that the stress is, because this is a long slender product, the stress is dominated by longitudinal effects that are due to local bending and of each wire component, and the extra addition that you get from the friction due to the slip between the wires and components. To be said, it is also having an ongoing PhD work that are focusing on some of these things related to the FME Northwind, and we are working to try to close some of these gaps that is relating to the constitutive modeling and the design criteria that is relevant. I also mentioned briefly these different local analysis tools that I have been involved in since early days, and would like to mention the Bflex also, which have had a lot of activities latest years due to the need for qualifying flexible riser products at deep water down to 3,000 meters, where we have developed quite a generic framework that allows you address effects like lateral buckling and where you can look at the cyclic development of these failure modes as a function of when the cross section is exposed to a combination of compressive axial force and cyclic curvature. This is something that develops over time, and as a result of this ongoing activity, there's also resulting functionality that has relevance to do stress analysis for other types of complex cross sections, I would say. Then I would also like to mention this. So we have several PhD theses that relates to this time domain model for vortex shedding loads, so that you add to the Morrison's equation directly, so that you are actually able to calculate the response as a consistent time series. And the advantage of the model is that it can handle both oscillatory and stationary flows, and it doesn't care whether the flow comes from the current or it comes from the floater motions, and you can also easily handle 3D flow conditions. So that is kind of something that is also ongoing activities in order to validate this model for a higher TRL level. We'd also like to mention the associated failure modes that relates to the operational phase, also due to cyclic loads, where in many of these components, most of the fatigue life is governed by the number of stress cycles needed to initiate cracks, because we try to avoid wells in the dynamic exposed section of the riser. And that means that most of the fatigue life is related to crack initiation, actually. And but of course, since inside these copper conductors you have metal contact between the layers, you might have influence of fretting phenomena also. And practically, that is dealt with by doing component testing to obtain a relation between stress range and the number of cycles to failure. So that is kind of the standard procedure, and of course another failure mode that might be relevant here is the gradual development of local component buckling due to temperature variations, and that might be quite complex interactions between gravity of the copper and the cyclic variation in temperature. So that is quite kind of things that we have seen for also similar failure modes that we have seen for flexible risers, and they have such kind of failure modes. They have a tendency of popping up as a surprise, and I would say that if you look at it from the overall perspective, what is new? Okay, the power cable is not new. The new is that you're using it for wind turbines, where you have a simultaneous action of dynamic loads and transient temperature behavior. So whenever you combine complex load conditions, you have a tendency of getting surprises. So that is, I would like to point out this, that this might be relevant also. We have done some research work into the copper wires, where the idea was, can we go from single wire component testing to the full conductor fatigue behavior by first principles, and they actually tried to do this. The thing is that we found that it is as we try to do SN data for single wire, take into account geometric irregularities, validated by putting it by constant tension and bending mode for a full conductor, and trying to find whether we were able to obtain component fatigue curves from the single wire data. And the thing is, we could not, because we have clearly the arc fretting effects coming into play, which basically says that you need to have to test the full component during at the realistic load conditions. Okay, I would also like to point out the static cable, because in some cases, if you don't bury it, it might be exposed to dynamic loads. And certainly, then if it is low gap, then you're having a dynamic stability problem. And if it is buried in the seabed, then you will have interaction with the effects that we have seen for pipelines. Buckling is one of them, and there's, if you have torsion imbalance and you are having this buried into the seabed, you might have gradual development of upward buckling, because if it twists, then you will lose the column friction and you can have this effect that pops, so that the cable pops up during a very high bending moment due to the resistance of the soil onto the cable. So that is, and of course, if it is left on the seabed, then you have exposed Morrison and Beeb, and then of course the boundary layer. So if it is shallow water, then traditionally we have neglected the boundary layer from if you have wave kinematics. But for low diameter products like power cables, that is quite conservative. So we are looking into this also with some industry projects in order to try to improve models for this hydrodynamic stability. And when does it go from a hydrodynamic stability problem to a VIV and Morrison load problem? Because that, of course, is something that happens over within a certain gap, so to say. And again, the same comments on the constitutive modeling is of relevance. And of course, the soil modeling is also for the power cable specific gravity is also something to have in mind. Because they are quite might be outside what is the validation range of the recommended practices development for pipelines, for example. Finally, I would like to just, I think, 3 minutes left, I think, if I'm correctly. So I just did an exercise, a student of mine, not myself, but a student of mine did an exercise using this time domain VIV model and to see, expose it to a dynamic racer where we just were looking at the tagging and hogging section and applied all the loads in one plane to just point out the importance of VIV, no VIV, friction, no friction. So just a relative comparison to see whether what plays a role. So that is that was some the data, environmental data taken from this. I think that is some open source Life 50 project, which is related to this Olav Olsen floating turbine. So we were and we applying the worst case environmental condition and so on, and we just took that from the report, and we were doing this global analysis in SEMA reflex and then exposed this to a moment curvature based model in this case using the VFlex program. This is a cross section that is open, that is published by Leroy in 2016. So looking at the fatigue in the wires in this case, the armor wires. So then, as a result of the steep water development of flexible pipe, it is now possible to apply these harmonic boundary conditions in VFlex so that you can model all the wires and process everything as a time series, because they're quite efficient. There's quite small number of unknowns in this analysis procedure. So we have a full model of all the wires, but assuming constant curvature. So then we were trying to see what is the fatigue life depending on if we include the VIV or not, and you see that so if it is dominated by cross flow VIV, then the minimum fatigue life is should happen at 0 degree with reference to this figure, and you see that that is actually what is happening. If you can see here based on the numbers here that VIV cannot be neglected, and of course neither can friction, and because they are basically for the VIV it's the stick domain, and very important into this assumption of the calculation, which I didn't mention, is that we have exposed it to the shrinkage stresses from the outer sheet, which then kind of lock the wires together to give this fatigue damage. again pointing out the importance of having good grip of what is the moment curvature behavior of these structures. Okay, then I think I am on schedule. I think to sum up, I'm pointing out the need for accurate constitutive models and the need to also then validate this by testing and so that we have numerical response models that are consistent with what we see. Bitumen behavior is always a problem because they're so temperature dependent. And of course, the description of the associated local failure modes. So when what is the load needed in order to actually create the failure, depending on whether the load is cyclic or it is static. And then, the loadout and this tool, this need for models to enable accurate calculation of what is the favorable route geometry, so you don't have these local failures during the loadout procedure. I think that there's a need for SN data by component testing because single wire testing is not very easy. So that is a challenge basically to model the realistic load condition. Then this role of thermomechanical coupling as the pointers, you need to have an investigation of what is the role of this temperature, this transient temperature loads into this. Pointed out the consistent treatment of wave and weave loads. Static, then this boundary layer of wave kinematic, that is an important factor actually. So that is, even if it's a static cable, you have some dynamic things to take care of. Shallow water wave models, that I know that is a big question in China because you're having some cables that goes directly into the shore. And of course, when we reach a minimum water depth, is our first or second order wave theories no longer hold. So that is, of course, a challenge. And then soil models that are relevant for power cable specific gravity and of course on bottom dynamic stability for sandy seabeds where you have coupling between, also you're having erosion processes going on and you're having things a living seabed and of course when do you then have VLV and when do you have this on bottom stability problem? That is something that have been a topic for ocean engineering as long as I have lived, but and we are not still in converging to a full model, I think. So, but so I think there's still work to do. So that was basically my presentation. Thank you for your attention.
Thank you, Prof. Savik, for your informative presentation. You have pointed out some very critical challenges faced by the development of power cable. And actually, there are two questions here for you. The first one is, which fatigue model is more suitable for the conductor fatigue assessment, SN curve or epsilon n? Thank you. This is the first question. Can you try to answer that?
I can try to answer. No, I guess also you also epsilon, you mean the strain number of cycle to failure, or you have stress number of cycle to failure. From my point of view, from the learnings from this PhD work that I was referring to somewhat there, I think as long as you transform everything consistently for practical purposes, I think this epsilon n is fine. But I think that if you transform everything consistently, it really doesn't matter from my point of view. But then you have to be consistent, of course, in your transformation.
Okay, thank you. Another question is how to calculate the structural damping of the dynamic cable.
Yeah, that is very much linked to the need for validation procedure, also the testing procedure. I have for many years, for tens of years, I've said that, okay, in a flexible riser or flexible pipe industry, you have to qualify the product by dynamic testing for a new application. And I was have been proposed to do a very simplistic test to obtain the moment curvature at different internal pressures. Of course, that is a key point because then if you have the moment curvature curve at different reference load levels, then you have the key in order to also evaluate correctly the damping. And of course, as long as you are having the correct moment curvature curve, then that you can include in your computation model directly. So you don't have to assume anything. Yeah, so this friction damping can then be directly integrated into the model. So then it's automatically taken into account. But you need to have this data because specifically for a power cable, it's very much governed by what is how you manufacture this, because the manufacturing procedure of the outer sheet, if it is an outer sheet, whether you have bitumen, which is temperature, so you need to have grip on what is the realistic moment curvature curve. That is a key point.
Okay, thanks.
You cannot obtain by first principle. You have to test it. And then implement it into the model.
All right, thanks. So any other questions from the Zoom attendees?
Hi, Savik. Yeah, nice to meet you again. Yeah, and I have a very short question. You mentioned there's a coupling effects between the temperature and the gravity in your presentation. So would you like to explain more about the coupling effects of the two loads?
Yeah, yes. So what might happen is that if you're having, because the different components of the cross section, they're having different elongation coefficients, and they also have different temperatures, because of it will be a temperature profile throughout the cross section during steady state, and then it will be a gradient also when you turn the power off if you have to close down the turbine, and then you will then have relative displacements that will then be able to kind of cause relative displacement. Also, you're having the gravity as an active force pointing downwards, and then you are no longer having the friction at some interface. Then one will start to slip downwards, of course, depending on what water depth that we're talking about. Large water depth, the more critical, because then you have more gravity load, and you might then have some depending on what you do in the top, you might have some extra onset of stress for one component and less for the neighboring component. And of course, if this starts to slide down, let's say that the conductor due to this temperature effect, and you take away the friction, it will fall down, and then it will have more compressive forces at the bottom. And you might then go into this local failure modes that relates to lateral buckling inside that for each wire in the cross section, or some bird caging effect, or whatever. So that is what I mean. And that is I'm not seeing this particular failure in operation, but I have a standing point of being suspicious, because whenever you are doing something new, a new application, where the new here is that you're having something which might in deep water, you have gravity loads, you are having dynamic loads, you're having temperature, so transient temperature loads, and then whenever new load combinations, we have a tendency of seeing that you're getting failures that were not seen before.
Okay, many thanks.
Okay, I think due to the time limitation, we should move to the next presentation. Okay, so the next speaker is Howard Chevy from 4 Subsea. Howard graduated from NTNU with a master's degree in marine structures, and he has 20 years of experience with flexible risers, umbilicals, and cables. And currently, Howard is a lead engineer in 4 Subsea on riser and cable cross-section analysis. Howard, hand over to you. You can start sharing your screen. Howard, are you online or not? So it seems Harvard is not online. Then maybe we move to the next speaker first. All right. So the next one is Nils Sodal from DNV. Nils Sodal, are you here? You can unmute yourself.
Yes.
Okay,
Hello.
good.
Can you hear me?
Yeah.
Yeah, I was.
Nils, maybe I
I was prepared.
introduce you first. Okay.
Yeah.
So Nils, he has 35 years of research and working experience in riser umbilicals and power cable technology. And his main field of work is consultancy and design assistance, qualification of new technology, failure investigations, design code development, and software development. Nils got his PhD also from NTNU in 1991. And he's currently the vice president in DNV, working in the section for riser and cables. So Nils, please go ahead. Thank you. So you can start sharing your screen.
Yeah, thanks. It's also a quick start because I was prepared to start in half an hour. I'm just struggling with the technology a little bit. Done? Oh. Yeah. Yeah. Oh. Hi. Can you see my screen? Can you hear me?
Yes, loud and clear.
Okay, fine. I'm struggling a little bit with technology because this is the first time we use Zoom. But thank you for the introduction. I was asked by Torgeir to give a short introduction to qualification of new power cable design by experimental and numerical analysis. And I've been glad to be invited. And also thanks to Svein for an excellent introduction to the complexity of the problem, which I think fits well with my presentation. Yeah, first introduction. As mentioned, we have, or as you are aware of, there is quite a lot experience with cables onshore. We have some experience with static cables offshore as well, and with in fact it's a large industry with wind energy. And now we are moving into a more complex problem with dynamic cables operated from offshore windmills. So we are now moving from the static part into the dynamic part. And if you look at the say overall big trends in this industry, the challenges we are facing is yeah, there are quite a few of them: larger capacity, longer distances, dynamic applications, also moving into harsher environment and deeper waters. And the market is also moving in parallel with a very fast need for new technology, and stretching today's technology. And also due to this growing demand, there is a lot of new players entering the market. And that has also a lot to say for how this technology is developing. And on top of this fast requirement for new technology, it's also a growing demand for cost reduction to have this in operation. Yeah, and technology qualification is say a formalism that we use, that's common sense put into a system to be able to deploy this technology. But as Svein mentioned, there is a lot of new issues to consider But we should also remember that all technology and components we use today has once been new and is now field proven by extensive research and development. So the technology qualification is really a vital driver for the technology evolution, as it enables development of a new technology into a challenging environment. And by this development, it will over time make it as a known technology. It's a continuous process going on, and in parallel, design codes are developed and updated. But by the nature of the problem, it's always lagging somewhat behind. So when you're going into with a new concept, you will not find everything in design codes. That's how it is. It's not particular for this industry. That's how it is in all areas. But when the standards and design codes are, in place, you can then safely deploy technology, fulfilling the requirements in those standards, applying known methods for known failure modes and mechanisms. That gives you, compliance with an acceptable margin to failure. That's how technology develops, regardless of the industry. And I just to have some background on how this goes, I can show an example from flexible pipes that I have been heavily involved with. And this example started as a Second World War pioneer application for fuel supply in the invasion of Normandy. And after about more than 50 years of technology development, it developed into the high pressure pipes that we use extensively today in offshore floating production of oil and gas. During this technology development, some serious failure modes, failures were experienced. They have in common that it's a complex failure mode that has been overlooked in design and operation. And there are also generic inherent failure modes specific for some of those products, resulting in very time-consuming root cause analysis, expensive replacement campaigns, and high cost and reputation impact. I have been involved in such an investigation myself. And just to give an impression of the efforts needed, we spent more than 5 years to finally conclude what was the problem. And the costs were astronomical. So now we are going into new concepts involving in the market. That's hybrid composite pipes. Now we apply the TQ process, as we call it, technology qualification process. We try to incorporate the learnings from previous work with flexibles and other structures into that to minimize the risk when we are deploying new technology. So that's how we are working with solutions, trying to minimize the risk of introducing new unknown failure modes. That's really the worst thing that could happen. Yeah. So I will give a short introduction to the TQ formal qualification procedures according to our RP A203, incorporating the learnings from previous work with this. And this is a work we do on a regular basis for various industry, but I mean, the learnings from the flexible, I think, is of particular importance for when we are talking about deploying new cable technology into the wind market. Yeah, this is the formal steps we go through in such a process. Define a qualification basis. That's what are the product we are qualifying, what are the boundary conditions, technology assessment, what is new, threat assessment, that's identify all the failure modes. Then we define a qualification plan, how to deal with all these threats. And then we execute the plan, and that's the formal qualification. And then afterwards we perform an assessment. Has everything been covered? And the main learnings we have gathered from the work we are doing is what are the particular important steps are technology assessment and threat assessments. And technology assessment, that's what is new. We define the components that's requiring qualification. And what we have learned is that we should have a particular increased awareness, not to exclude anything. I will come back to why that's important. And threat assessment is the second one. That's very, very important. And Svein gave us an introduction to the complexity of this problem. And the issue here is to identify failure modes and mechanisms. And it's we are used to do a traditional component-oriented FMEA, that's failure mode and effect analysis. Then we go through every component and say what can go wrong, what can threaten the function of that. But in addition, we find it very useful to use what we call a scenario-oriented FMEA to capture development of more complex failure modes. Because knowing the failure mode is basically everything. That's the basis for the qualification plan, and that will not be complete if something is missed. And this might lead to overlooking very, generic failure modes with the product. And that's exactly what happened with the flexible pipes. Yeah. Technology assessment. Define what to consider in the TQ process. That's identification of new technology issues not addressed by existing design practices or standards. And here we should be very, very careful not to exclude seemingly harmless modification as a new technology, because small modification can really make a huge difference. We also seen examples of modifications that has been introduced to improve performance, but in fact that was not considered as critical, and really instead of improving the technology, it introduced new failure modes. And the assessment of the technology assessment shall be based on documented track records, and not say standard phrases as this has been used before and will not have any influence. Should be very careful to take everything into account. And if you are in doubt, just include it in the TQ scope and close it out later. Yeah. In a traditional FMEA, it's that's component oriented. A typical work process for that is that the technology is broken down to components, and the function of each component is identified, and the threats are then identified as mechanisms or issues that can leading to loss of function for that component. And that's a fundamental process for failure mode identification that you always shall do, and should always be the starting point. But for more complex failure modes, as we easily can have for cables, this pose some challenges. It's for instance, interaction between components, interfaces, capture the influence of time-dependent degradation mechanisms, and that could be say mechanisms that's not is a failure mode in itself, but could over time lead to loss of function. And we need therefore also to capture a timeline of failure mode development. And very importantly, cover manufacturing, installation, operation. And this is doable within the framework work of say component-oriented FMEA, but it's very difficult to do. So we have therefore introduced a new way of thinking to capture the development of more complex failure modes. That's what we call scenario-oriented FMEA. First, we start with this traditional component-based, and then we go further, where we focus on possible complex failure modes. We build then on the component-based FMEA identified earlier, and we identify scenarios leading to loss of functions. Considering timeline of failure development, that's a sequence of events, manufacturing, installation, operation, interfaces, and capture the influence of time-dependent degradation mechanisms, aging and temperature, and there's this example with the cable core, with also having some influence from weight of the components. And this is the working process here. It's not that formal. We try to gather multidisciplinary competence, and we have then say more creative setting where we go through every failure mode and see what through the lifetime of the product, and see how the different other mechanisms can influence the development of the failure mode. And we found that very useful for when we're working with flexible pipes, and this is extensively used now when we are trying to qualify composite pipes. Yeah. Then we could have some words about what to expect for power cables based on what we have recorded of failure experiences, and where we think we should really focus to meet the industry challenges. We have some failure statistics on work we have done in joint industry projects in DNV together with the industry. The figure on the left show the recorded rate of failures for different categories for cables all over. It's land cables and also some static offshore cables. And what's really is dominating is manufacturing, installation, and also some on design. But still, it's manufacturing and installation is close to 50% of total failures. We have fewer data for subsea cables, and their manufacturing is even more important, and installation as well. And together, that's 70% of the total recording failures so far. Yeah, and if you go further to break down what has happened, it's the cable cross section itself that's has experienced most failures, about 85%, and of those, 74% is mechanical failures. So mechanical failures for the cable cross section itself is dominating from the statistics we have available today. Yeah, dynamic power cables, little experience, so we really don't know the distribution of failures. But of course, we have also, as Svein mentioned, we have a lot of experience for oil and gas. Similar products have been operating for decades, such as umbilicals, power umbilicals in particular, also direct electrical heating cables, and so we have a lot of experience that we can use from offshore. But also we should keep in mind that today's failure statistics show a high number of failures, but the experience is mainly from static cables. And of course, dynamic cables is more complex than static cables. We have different types of failure modes. We have extreme loads, effects, fatigue, wear, and also more complex failure modes. But the electrical design of a dynamic cable is quite similar to static. So it's the mechanical issues that really is the main challenge for dynamic cables. Yeah, focused areas, some recommendations. It's based on what we have today, but manufacturing, as I said, cable cross-section mechanical failure modes is dominating today. Manufacturing is also an obvious area of improvement. But we should keep in mind that the reported failure rates may be somewhat influenced by quite a lot of new companies entering the market. So we should be quite company specific when we look at threat assessment based on previous track records of each company. For threat assessment, we should definitely look into the scenario-based FMEA, in addition to the traditional component-based FMEA, covering manufacturing, installation, operation. And we should really consider how in the scenario-based FMEA, we should really consider how these possible manufacturing imperfections within the defined tolerances that you have for each company might influence the failure development for each installation operation. When it comes to qualification plan, that shall define all the actions needed to mitigate all identified threats, and that will be a due balance between test and analysis. And it's also very important that there shall be a transparent link between failure mode and each qualification activity. And that includes testing as well, because you should always define exactly which failure modes that challenge in each test. Yeah, and in this you should also include activities to qualify the engineering design methodology. And that's such as validation of analysis by testing. And you should also be very careful to define the limitations for each methodology you define. And I mentioned that there is a requirement to be this growing demand, and having qualified the design methodology will give us the opportunity to launch technology in shorter time to the market. And as the TQ experience is built into the design methodology. Yeah, and this also is a discussion: should you qualify by testing or analysis? But in fact, you need them both in parallel. There is a mutual dependency between test and analysis. Test is needed to validate analysis, and analysis is needed to define the test conditions. This really needs to be incorporated into the TQ process. It's because it's essential to obtain reliable results. One example is full-scale fatigue test, and where the objective is to expose the critical element in a cross-section to a target fatigue damage, typically up to 1 or 0.1, for a realistic operational fatigue loading environment. That is the environment you are expecting in operation. Analysis is therefore needed to define the test conditions. You need to accelerate the fatigue loading to meet this target within a realistic frame of the test, and also just to identify the critical element in the cross-section that's not obvious. But in parallel, you need to do that, you need to have a validated analysis approach in place. That must, of course, be validated by testing in terms of stress, strain, fatigue calculations. So there isn't, you need both in parallel. You can do, of course, everything by testing, but that's not, say, efficient way forward when we are launching new technology into the market. Yeah, some concluding remarks. Yeah. A thorough TQ process, if done properly, will contribute significantly to reduce the risks involved. Knowing the failure modes, mechanisms, and how they develop over time is really everything to be able to launch a product. Threat assessment should include both component and scenario-oriented FMEA. And this will, if you do this properly, this will also contribute significantly to reduce the product risk as it's very, very expensive to discover something late in the process. It might seem to be comprehensive, but it's a small investment compared to possible consequences of overlooking any failure mechanism. But by doing so, we should also be a little humble, because we can reduce the risk significantly. But regardless what we do, there will always be a residual risk, and that's the risk of deploying new technology. Okay, thank you for your attention.
Thank you, Niels, for your interesting presentation. Let's see whether there are some questions for you or not. Okay, there's a question. Can you give us insight into the kind of design failures you have encountered?
For yeah, I mean, it's this is an activity we do, say, as a regular project that's offered to the industry, and we have, of course, been involved in a lot of different failure modes. But the worst one is, say, the generic failure modes that not has been addressed in design or operation. There are a lot of examples. One of them is what I mentioned, what I worked with for 5 years was something called carcass tearing in flexible pipes. And that required replacement of, I think, 50 or 60 flexible pipes in the North Sea. And that was simply related to one specific product, but it was a huge consequence because that was a complex failure mode that was overlooked. And we also have seen failures in umbilicals, not that serious because umbilical is more tailor-made, and you can, it's not that big consequence because you don't have one specific failure mode for a product that's used for a large number of installations. But we have seen this for many industries, not only flexible pipes and cables, umbilicals.
Okay, thanks. Any other questions from the Zoom? And if there's no question, okay, there's one more question. It is so good to see you well again. I want to ask a question. Compared with oil and gas applications, do you expect any special failure modes or dynamic behaviors for the dynamic cables used in the floating wind turbines?
I think it's the combination of the market setting with what I think is a really huge risk is that the new companies are delivering cables to the industry. Maybe with less experience due to the market, strong drive in the market to deliver cables. So, and I think that's why we have so much failures related to manufacturing. So I think it's the combination of say cost reduction, new companies entering the market, and a complex product. I think that's this combination is the biggest risk for the industry.
Okay, thanks for your answers. Any other questions? Okay, if there's no more question, then we give our thanks again to Niels for your excellent presentation. And for your information. Sorry?
Hello? Okay, sorry if you can hear me. Let me just, I asked a question, but I just want to say this, I couldn't write. Given the high number of failures due to manufacturing, and knowing that testing plays a key role, I would like to understand whether the tests done are not enough. If they are enough, if they are not, is it as a result of tests that are not properly done with respect to FAC, factory acceptance tests, or site acceptance tests? What I mean is, we have a lot of failures due to manufacturing, and if FAT had been done properly, maybe those failures should have been seen before even it gets to the site. So what I'm saying is that the kind of failure we see resulting from manufacturing, was it as a result of inadequate FAT or SAT?
I think, what I have seen have been quite, what I have seen so far is companies that deploy technology not using to address specific challenges related to dynamic cables, and it's quite fundamental or basic things that's been overlooked. So I think we can gain a lot focusing on, say, manufacturing requirements, and see also, say, it's a big difference making dynamic cables than static cables. It could be quite easy, say, basic things such as extruding sheets that's not properly suited for dynamics. It could be use of improper fillers, for instance, and quite basic things that has given failures. So having focus on, say, basic manufacturing requirements is important to avoid unnecessary failures.
Okay, Niels, there's another.
Thank you.
There's another question.
Thank you, I'm just.
Sorry, you continue the discussion.
I said thank you. I just said thank you.
Okay. Yeah, there's another question. Any experience about life extension methodology for dynamic, flexible cables or risers, I think?
Yeah, for risers, there's a lot of experience, but for cables, it's dynamic cables operated from windmills. It's obviously less experience because we are just entering this market. But yes, for risers, there is a lot of experience and what to consider. And the problem there is, what is the status of the product you have today? And that also goes back to the failure modes. You need to know what has been, say, challenged in operation, and say what is the residual life, and you need to know also the failure mode. What is for instance, what is the problem? Is it, for instance, fatigue? How much fatigue capacity has been used so far in the life? And then you do an assessment. But it's also someone here also mentioned instrumentation and say surveillance of the response that could give you any indications of how the product has performed, and that will of course be a basis for life extension. Also, say, inspection. So has there any signs of external damage to the product? Has the product been used outside the design envelope? Is it excessive marine growth? The whole track record of the product up to now. And then you can do an say, engineering assessment. What's the residual life of that product? And I think we should then use the same methodology for cables as we do for other products, basically.
Due to the limited time, we need to move to the next presentation. And for information, Harvard Chevy from 4Subsea, due to an unexpected reason, he cannot attend today's workshop. So we will directly move to the subsequent speakers. So the next speaker is Professor Zheng Gao from NTNU. Professor Zheng Gao is the professor at Department of Marine Technology, NTNU, and from January next year, 2023, he will join Shanghai Jiao Tong University as a professor. He obtained his master's degree at Shanghai Jiao Tong in 2003 and PhD degree at NTNU in 2008. And currently, Prof. Zheng Gao is mainly working on coupled analysis of bottom fixed and floating wind turbines for design and installation. More specifically, it includes numerical modeling methods for both global loads and local structural response analysis, and numerical simulations for installation of offshore wind turbines with focus on wave and response forecasting and motion reduction control during marine operation. So Prof. Zheng Gao, please go ahead. Thanks.
Yes, I hope you can see the screen in full size, right?
Yes, very clear.
Yep, good. So I will just present some information about global motion of wind turbines, and especially mention some of the challenges when the floating wind turbine might be interconnected. And this, of course, provides a top-end motion for power cable design in connection with the direct loads on the cable. I also would like to thank the colleagues here for their contribution. I will very briefly mention the offshore wind activity in general at NTU since 2008, and then have a bit talk about floating wind turbine, the trend, especially with larger turbine size. And then I think we have very good knowledge now regarding single turbine dynamic analysis under simultaneous wind wave loads, but there's a lot of challenges regarding farm design analysis. And also, previous speaker has also mentioned the installation cable is an important perspective for wind for design. And I will also briefly mention this. But in that case, actually, we are mainly working on marine operation related to the turbine installations. And in recent years, we are also interested in direct wave measurement and the deterministic wave forecast, how they can be applied in such operation, which could also be relevant for power cable installation. Here you see some faces, and you already see two of them, Torge and Sven. And since 2008, Torge initiated some offshore wind activities in Department of Marine Technology and NTNU. And then basically we focus on developing numerical method models for global analysis of wind turbine, bottom fixed and floating ones, and duly normal operation. And then in recent years also look at the installation process and using numerical simulation for especially to identify the allowable sea states for operations. And then we also have people working on components, like me working on job chain, and Professor Smith-Savick working on power cable. And in connection with, in cooperation with Think Tank Ocean, that also model testing work basically on global analysis of wind turbine, floating wind turbines. This is very short. Just also just to bring some recent trend regarding the size of turbine. Of course, Professor Mo mentioned that the installed capacity will increase because of large use of wind power in general. But actually, for individual turbine, the size also is getting very large, especially in the last 10, 15 years. So we are already talking about a market size of 10 to 12 megawatts, and then the upcoming 15, 16 megawatts. So the main challenge is that the single blade is very long. It's already 100 meters long. And this brings, of course, a lot of aerodynamic aspects, coupled analysis challenges, and also installation challenges. And so, but that is, anyway, all the design of the floaters, even marine lines, power cable, they are really governed by the trend using larger turbine. This cannot be stopped. We cannot go back to small turbines. So this is an important feature for future development. Regarding floating wind turbine, there's of course different concepts based on how hydrostatic stability is achieved. And the popular ones are spar semi, which has also been heavily widely used in oil and gas industry. But the displacement of those platforms are very different. It's quite small for floating wind turbine. If we are looking at the 5 to 15 megawatts, we are talking about displacement of 5,000 to 15 or 20,000 tons. So that is and the TOP has been not very well developed as prototypes because of the challenge for installations. However, we also see other type of structure, because basically we don't need buoyancy element stored for storage purpose. So then there's other type of concept, especially this truss type floating concept has also been developed. And this is also, of course, more challenging regarding fabrication, fatigue design. So, but they might be good also for reduce the overall cost for further development. Here, basically showing the prototype has been in water or still in water, and the two from China, semi-submersibles. One of the challenges from the beginning of designing floating wind turbine is the coupled analysis. So here we basically looking at the wind loads on blades and the couple wave loads on floaters and coupled due to motions. And since 2005, there are many code software has been developed. And of course, there's always a challenge, as I mentioned, when the turbine size is getting larger. So from the beginning, this alloy elasticity has been a bigger issue for slender blades. Another aspect is the control that directly applied for regulating the power and reducing the loads. And so at the end of the day, we have to use direct calculation and design based on first principles, and preferably using time domain simulations. Those are basically global analysis, and that provides, as mentioned, the boundary constraints for power cable design. But in fact, that it is possible to include the power cables in a coupled simulation framework, similar as for mooring systems. As I mentioned, from 2005, there are many different codes. Some famous ones are fast, Hawk2, Sigma, Bladed. And another challenge is that since the analysis problem becomes complex, reducing the user error has become very important. And there's actually a lot of comparisons that has been made using same software, but different users end up with different results. So at least like DMV, they are streamlined those analysis, and both for global analysis, also later for global design or floaters, mooring lines. So these are very important aspects. Some of the basic floating wind turbine characteristics is important to understand before we use them for power cable design. And basically, we have wind loads which induce quite large, but also very offset due to different mean wind speed. And here is actually showing the truss force, the horizontal truss force, due to different turbines rated power. Basically, you could say the truss force linearly proportional to the area of the rotor, and also linearly proportional to the power. And for very large turbine, then there's also control entering this. It's called the peak shaving, which actually reduces the power truss peak, especially around the rated one. So this is also to help for design of the mooring lines and also the floater from static stability point of view. However, we have also large resonant motion, especially due to wind loads, slowly varying motion. These can be both surge and pitch motion. And then we have more independent wave-induced loads. So these typically aerodynamic damping has a limited influence. So that means in order to reduce the platform motion, reduce the dynamic loads on the power cable, you need to have a good hydrodynamic design of the floater. Wind can also induce tower in photo vibration, but they are typically high frequency and with small movement, so they typically do not influence the top end motion. Here is just showing some of the results for operational condition, which is typically governed by wind loads, and parked condition, which is wave loads contributes significantly. From the power cable design point of view, actually the mooring system design is very important. So this mooring system provides a good balance between the offset on the main wind loads and also the dynamic loads due to slowly varying motions. And typically, we are now using only 3 lines for each turbine, so there's no redundancy. And very likely for larger turbine, when the size of mooring line getting larger, if we use only one, probably we can engage to use 2 lines in one corner, which also actually introduce redundancy. However, there's a lot of challenging for relatively shallow water in the order of 50 to 100 meters, which is also relevant for floating wind turbine. And then some sites, we are not entering in very deep water area yet, but if so, we have to use very light material for mooring lines. And basically, we cannot introduce too much buoyancy in the floater to reduce the loads. Another aspect is that wind farms, they typically have many units, and then they needed to be connected somehow. And like in high wind turbine, they use a shared anchor. So mooring lines, they are not directly connected, but using such an anchor for shared points here as seen here. There are 11 8-megawatt turbines. Here we have done some work in connection with the Marina project. Sven has a PhD student work on that. This is actually a combined wind wave concept. And when we get the motion of the end platform, then of course we can introduce the top motion for power cables. And then you have consistent wave and current loads on direct line cable to do the dynamic analysis for power cable design. And as Sven mentioned, there are a need for nonlinear constitutive model for when we model the power cable as a beam for global behavior. And of course, the curvature and the tension are major challenges when we are looking at from the global point of view. Regarding the dynamics, here is showing some of the examples. What is important in shallow water is the location of the hand-off position. It is beneficial to have a higher hand location, and also for larger water depth, it's more easy to accommodate dynamic cable design. These are just showing some of the snapshots. Typically follow a quite static behavior, but locally you may have also dynamic behavior due to the combined motion and loads directly on cable. This is not the end of story, just looking at one turbine. So one of the challenges facing this industry is that we have to use many units in the farm setting for commercial development. And then there's a challenge related to scale in space and in time. But at least the trend is now to integrate turbine level analysis, but also farm level, the wake analysis and so on. So that is some new research direction is important to observe. Of course, when we connect a turbine together in a floating wind turbine farm, of course, we are talking about a relatively large horizontal scale in the order of 5 to 10 kilometers by 5 to 10 kilometers. So the incoming wind wave condition might not be homogeneous and coherent. So there's also need to get more data regarding this. There might also be direct interaction between a wind and wave in the farm level. Of course, the focus now has been the aerodynamic wake effect, which includes basically dynamic loads on the downwind wind side of the turbine. And there's also a proposal of shared moorings, and like from SEMA, a Norwegian company, here you have mooring line connected with shared mooring line, and which is also anchored to the sea bottom. And you can also imagine if we have power cables, they need to somehow also connect it, which have become a very complex network. There has been some recent work showing those behavior of the wind farm in a interconnected framework. And this study was done by Ho from NREL. This year, it is using 10 turbines in different configurations and end up with this type of configuration. And the basic idea is that the sideline is similar as what we used for single turbine. And then the interline, they only connect with horizontal line. So basically, they reduce the line length for vertical parts to reduce the total cost. However, this creates a very complex interaction between the turbines, and especially there might be also phase difference between the turbine, not only wave-induced motions, but also slowly varying motion, which can induce very large tension in the inter-array line. And the side line then needed to take really the total loads on the wind turbine in the whole farm. So it's also create a strong demand for the side line for this purpose. But if there's a one line failure, there's a benefit to have them interconnected regarding the offsets that are induced by one line failure. As I mentioned, typically we have only 3 lines for one turbine, and if there's one line failure, even without loads, there will be large offsets. And then if you have still wind loads, offset will be very large, so that you have to disconnect the power cable, or the power cable might be damaged. It might be also in collision with another surrounding turbine. Well, if you have connections between them, it reduces this offset. But these are just concept study. It's still not very clear how the industry will develop. It's certainly related to the water depths and also the reduced costs that we may have when we interconnect those lines. Some words about installation. Basically, we are talking about export cable, where you have to install onshore, say from the cable installation vessel, and then pull into the shore grid connection. And then there's of course a lot of time spent on this cable laying activities, where also the cable might be buried afterwards immediately. And then you can imagine that they are not in calm water during the installation. So different wind wave, especially wave-induced vessel motion, could be challenging to control the tension level during installation and cable laying activity. And then at the end of days, this needed to be connected to the turbine or to the substation, where typically we use additional lines. If we have the turbine already there, where we come with the installation power cable installation vessel, you have lower down the power cable end, and then with winch to connect it to the platform. Or if you install the turbine cable first, you temporarily locate it with buoy and then pick up again. Here I just want to say something about operation simulation. We are mainly focusing on turbine installation itself, blade installation using jackup or floating installation vessel. But the main purpose is to derive the operable sea state by using response-based criteria. And this is typically you do in planning phase, where you simulate waves and dynamics and also get responses, could be motion or stretch responses, and then using a limiting criteria to define under which sea state you can do safe operation. Well, in the real execution phase, there are different ways. You need to use first the forecasted weather, so that they can be compared with the allowable sea state to decide whether you start or not the operation. That is a relatively long perspective, say a few hours or 1 or 2 days. And then if we have a short perspective, like a few cycles of waves, then you need to measure the incoming wave field and forecast the wave propagation and forecast the response in order to use, say, motion feed-forward control during this operation. This is typically for blade installation. We can introduce this control perspective. So here at SFR MOO, we have also been working on this. And there's a bit challenging when we have to measure the wave as compared to simulated wave, because in simulations, you simulate the whole wave trend. But the measurement is only up to current time. There's a limit that we can forecast the wave to the future in terms of measure the space and the time. And then another issue is that using the incoming wave, there's also needed to have dynamic motion analysis, where we have to assess the causality, dynamic memory effect, and whether the input is sufficient or not to provide the responses. So that is the basic framework which could be relevant for blade installation or say access to turbine for maintenance or the power cable installation. I will not go into details the way to do wave forecasting, but essentially we are also doing forecasting when we design a structure, but it's more like a status perspective. We don't care when the largest wave will come, but in operation, it is really important that we should know the incoming waves. And basically, we can use wave radar to cover a certain range, typically 1 to 2 kilometer area, and so that you can forecast, say, up to 2 or 3 minutes the incoming wave, and then use it for control purpose. Beyond that, it's too far to measure accurately the wave, so you have to forecast the sea states and use the, say, long-term decision making. There's also some campaign in SFR move, so it's using the anti-Gunner's vessel where actually we rent the mirrorless expand wave radar for some time. There's a measurement campaign near Olesund in the solar field, out this entry of the field and inside the field during April this year. And general observation is that we have large swell during that day and a relatively small wave inside the field. And here is a comparison of the spectrum that is measured from the wave radar, but also there's a buoy measurement so that it's possible to compare. But as I mentioned, that the wave radar image typically give you snapshots every every 2 seconds, so you can have a range of say 1 to 2 kilometer by 1 to 2 kilometer area regarding the wave components, and then it's possible to decompose this wave components for development to the vessel position. So we are still working on that. But essentially, regarding the wave forecast, in very short time, within 2 or 3 minutes, there's limitations, and that is we have to assume there's a pure wave propagation problem, so that wind forcing is not affected the wave field, and the measurement size accuracy is important to give as input. Then, as we know that the different wave frequency, a wave with different frequency, they travel at a different speed. So you will never have a repeated wave signal if you are outside the wave measurement area. So that is some limitations we will have. Typically, you can see that this is a measured wave time series, say wave radar in space, and we want to have a wave in this location, but the short wave travel slow, long wave travel fast. So it's only in this triangle we can do deterministic prediction. If it's outside, so that means for this point, it's from this time to this time. This axis is time. So that also gives some idea about what we can do or we cannot do for wave forecasting. When we get that, of course, we can also forecast the motions and to do control during installation. Here we just use some simulated data to show how good this simulation wave forecasting could be. Here is just the measured wave at this time, T0, and we want to know what is a wave which will propagate from this direction to target level 0. And here we are only using the time snap at T0, and then reconstruct a wave and propagate in time. So here you can see that in the beginning, you would not be able to predict a wave because the wave hasn't come, the measured wave have come. But after time, you also will get a very accurate wave. Here, blue is the actual wave and the red is the predicted wave. And then with new wave come in, of course, you have to use the new wave snapshot in order to do this. But here we only use what happened at T equal to 0. So there's a process to continuously process the data in order to do the prediction accurate in time. Okay, I think I'm using too much time now. Just to conclude, I just briefly mentioned the motion analysis for single turbine, and then a challenge related to the floating wind turbine when they are interconnected. And then also briefly mentioned the power cable installation and the other installation activity for wind turbine, and our current activity on wave forecasting and so on. Yes, thank you. If you have any question, I'm happy to answer.
Thank you, Prof. Chen Gao. There's actually a question. Is there any limitations on the offset water depth of the offshore wind turbine? So about the offset of the limitation of offset of offshore wind turbine.
The horizontal offset is really determined, you could say, by the power cable design. And of course, the strength of the monoline design is also matters. But at the moment, water depth, I think we are using, well, there's not so many prototype floating wind turbine anyway, but it is from up to 200, 300 meters. That is the range for current design. But if we go beyond, say, some area with very large water depths, then as I mentioned, you have to use light monoline material in order to achieve a better floater design. In principle, there's no limit, but in reality, there's a cost issue.
Okay, thanks. Due to the time limitation, I think we need to move forward to the next speaker, Dr. Naichen Ye from SINTEF. Dr. Ye obtained his bachelor. Okay. Sorry, there was some misunderstanding of the questions just now. So the question was the limitation on the offset over water depth. So the ratio of offset and water depth. So maybe you can comment a bit on that, Prof. Chen Gao.
Yeah, I can come back to that. I think, as I mentioned, still it's related to the design of power cable, what is allowable, say, near and far offset due to the tension and also curvature requirement. So I think generally, in most cases, we are talking about mean offset, say 10 to 20 meters on the mean, largest mean thrust force. But it's really depend on the design of mooring system that which should limit this offset. But yeah, but mean offset is one issue, but dynamic analysis is more important, as I mentioned, because of different frequency contributions. Yeah.
Okay, thanks.
Yes.
Sorry for the interruption. Then I continue, introduce Dr. Ye. Okay, Dr. Ye obtained his bachelor and master degree at Shanghai Jiao Tong University, major in naval architecture and ocean engineering. And he got his PhD in marine technology also at NTNU. He has been working as a research scientist at Marine Tech since 2003, with the main focus on structural behavior of subsea umbilicals, risers, flow line, and pipelines. He's currently the research manager in structural engineering group at SINTEF Ocean. Okay, Dr. Ye, please go ahead. Thanks.
Okay, I thank you for the introduction, and nice to see you, Professor Wan. I haven't seen you for quite many years, 10 years around, since you left.
Not that long, I think. Yeah.
Okay, I share my screen now. Is it working now?
Yes, we can see clearly your shared screen.
I'm going to talk about the mechanical test of dynamic power cables from component to product level at SINTEF Ocean. And I think before I go into the technical details, to say a few words about this workshop. I attended quite several conferences and exhibitions this year after the summer, actually. You know, OMAE, that is more academic. And then SIGRAE, I met oriented people there, and also this global offshore wind at Manchester. And then I think, Niels, you were in the floating offshore wind. I heard your talk there, but I didn't have a chance to talk to you, but it's nice, very nice to meet you here. And,
yeah, thank you.
Yeah. And I think this workshop is very special, actually. All these workshops and conference I attended this year, I think if you look at the power cables, this workshop is very unique and specific and quite strong team from an academic level to industry level, and also the DNVs here. I think we are, if you compare with all these conferences, I think this workshop is among at the top. So congratulations first for organizing this workshop. And then I go into the details. You see, this is the full picture of we'll talk a lot about offshore floating wind. And then you can see, you can from the aerodynamics, and then you have the floater motion, and then you have the floater cable interaction, and the cable itself, the motion, we talk about the vortex-induced vibration, and Professor Savik mentioned about the B-flex and the U-flex. That is for detailed cross-sectional mechanics and the stress and fatigue. And then also mentioned the stability of the cables on the seabed. There also, I think, Sven, you didn't mention that the software you developed similar, that is for laying and stability of the cables and pipelines on the seabed. But if we start from beginning, when you design as Orient cable, you design your cable, and then you need some kind of tools, and then you need to simulate that by using U-flex. And then you go into manufacturing, you have your factory, and then how to simulate the manufacturing process. And then you go to the field where you install the cables, and then how to simulate the cable installation is also a challenge. And then if you look at the titles today, Niels also mentioned that you need to not only numerical, you need to test that. So testing covers a full picture of the whole lifetime of the cable. You need to test the behavior in the waves, in current, and then also mechanical testings. And then in operation, you have the fatigue, and how to ensure that you have sufficient fatigue life. Then you need to test that in a lab. And then you have all these kinds of mechanical failure modes, from fatigue and ultimate stress and outer sheaths, all this kind of bird caging, buckling, all these kind of mechanical failure mode you need to capture. Of course, you can do numerical analysis, but the one that you are so sure is that you have to perform test. Think about the SpaceX. We have been seeing a fantastic review of SpaceX. And then if you are now in Norway these days, yesterday I went to another location with the Petrobras, and we sit in the taxi, and then the taxi stopped on the icy road with a little bit of slope, and then he could not stop again because of the friction. So what is the friction actually? According to physics, friction is not independent of your normal force, but actually if you stop your car, you cannot start again, even though the physical formula is the same. And Sven also mentioned the bending stiffness of the power cable. What kind of stiffness you are going to use in your analysis based on your nominal value, or after the fabrication, do you know what is exactly the bending stiffness is? Actually, you have no picture on that. If you test, you will find that that is several times larger than your nominal value. And then you are using the nominal value in your analysis to calculate fatigue. All this cannot be captured without doing testing. Mechanical testing of power cables, you can see you can perform full scale, where I think Sven also mentioned that, and the mid scale, where you have the component, and then small scale, like the copper conductors, the copper wires, the sheath layers, and all these feelers. And then you have to test that in different conditions, where you are operating in seawater, where you have the CO2, H2S, and the nitrogen. So all this must be documented by performing a lot of testings. And why full-scale testing? You need to qualify, as Niels mentioned, you need to qualify your new design. And if you have existing design, but you want to apply to a new field, then you also need to do tests to qualify that. And then you have a new design methodology. You also verify how to verify testing. And then you want to develop an analysis tool as U-flex and B-flex similar, how to make sure that your analysis results are correct, testing. And then in operation, how you are sure that your operational condition matches your analysis testing. So testing actually covers from your design to operation. In order to get knowledge about your products, you need to instrument your testing. So confirm your loads and then detect any failure. So you can see, I will not go through all the whole list. You can get this PowerPoint afterwards from the workstation. And then for power cables, especially, you need to monitor the continuity of the resistance and then conductor resistance and insulation resistance, and also make sure that you can still tolerate high voltage after the testing. And also need to know when the wire breaks. So there are a lot of testing instruments. This is a very detailed instrumentation, and that is the key competence in every lab. I think Professor Fu is here for your hydrodynamic testing. Also, this measurement is more important than your design of your testing. So it's very much technical details. And for your full scale testing, it's very expensive. If you test 3 to 4 months, it will be around 3-4 million. And then if you test to 1 year, then you can see. If you think about the electricity price in Europe now, I think we cannot tolerate testing for 8 months with 500 kilowatt per hour capacity. So this testing is very expensive. I think we cannot perform testing now when you have a price each kilowatt hour costing about $1 now, $1 US. Think about the cost for this testing. So that's why we must be smart and clever to reduce the amount of testing by design, analysis, and combine with its instrumentations. And we also see that the picture, Torige, you also show this picture for your first slide. The compression of the power cables is a very important issue because it's light. When you touch down the seabed, you'll get compression, then you'll get the buckling or the damage of the cable. And you can see different failure modes due to compression. And we have built a compression test rig to know how much level of compression your product can tolerate. According to DNV, you are not allowed to have a compression level during operation, but it is there, especially during the installation. Yeah, I will not go into details about you see this rig is there, and then you can perform the compression testing, bending to a certain level of radius based on your analysis, and then apply certain amount of compressive axial load. And here are some animations. You can see how many testings it is there. We have compression, full fatigue, and also in the hydrodynamic testings concerning VIV. And we have built a structure lab, and then many of you have been here, especially I think Orange people, you are here as well. We operate the lab together with NTNU since 1978, but now we are moving to a new location. The new lab will be in operation February next year. So you are welcome to visit this lab. And then what kind of testing we will offer in that lab? For full-scale dynamic fatigue tests, as usual, we have 2 full-scale test rigs for power cables and flex risers and bellicles. And then we'll be able to perform bending and tensile and the characterization testings, and also compression testing. The new testing facility will be available there is the bending stiffness testing. It's a traditional, but we need to know exactly under certain level of axial tension, what is your bending stiffness? And then you must iterate your global analysis by using the actual bending stiffness under certain level of tension. So this is quite a new test facility, and then you will see that even though you don't have any tension, but you still see significant hysteresis due to the fabrication process of your product. And then you need to know that to do your global analysis to predict fatigue life. And then another very wonderful testing facility will be torsion testings. Professor Savik also mentioned this cable is not perfectly torsion balanced, so you will get some kind of torsion, and during the handling of the cable, you will see torsion has caused millions and millions of dollars of loss to the manufacturers and also to the operators, delaying the operation and then delay the installation. So this torsion test rig will be unique in the world to know exactly, and we also will develop, of course, numeric tools to predict the torsion, but in order to make sure that the prediction is reasonable, this torsion rig will be very critical. And for flexible risers, I think it is not as much relevant to here, but just need to know that we are performing different kind of mechanical testings for flexible risers as well. I think since we have been running out of time, I will not go in to too much details on that. I'll leave you some minutes for questions. Okay, I think I stop here. Professor Wan.
Are you sure? Because I think we can shorten our coffee break time. It's okay.
Yeah.
Okay, then maybe we can have some questions. Any questions from the Zoom audience?
Back to this picture.
Hi, Professor Dr. Ye. Nice to meet you again. And
nice to see you here, Professor Yan.
Yeah, and nice to hear you will move to the new laboratory next year, and hope to we can find some chance to visit there. My question is, you mentioned that the fatigue of the conductor of the marine cables. Can you explain a little more about the fatigue about the conductor?
I can, yes, I think the fatigue of conductor is a very complicated issue. Sven has had one PhD student about 10 years ago, worked on how you make use of the single wire test data, and then by combining that with some numerical analysis, then you have some kind of scaling effects. Then you can make use of the single wire test data to conductor level S-N curve data. And then how to correlate that? That is a challenge because each manufacturer, they have their own packing process for the conductor. Then how much you pack the round shape wire into the hexagon shape, then you need to perform testings to verify that this correlation factor is correct. That can only be done through testings. Professor Savik, you can comment if I miss something. I think that's the only way.
I said something about that. I concluded that you cannot do it by first principle. To be more precise, we concluded that in order to get the relevant data for a full conductor, you need to test the full conductor under realistic condition. It might be that because we were only including longitudinal stresses in our evaluation, and of course it might be possible by 3D finite element to see whether you can correlate better by looking at some critical plane methodology, for example. But then, of course, you need to have a very, very expensive computational model in order to evaluate this on the local contact. And of course, you're having, then you will need to, first of all, simulate the realistic compacting procedure of how this is manufactured, also how it is put together. Then after you have done that, you need to expose it to fatigue load and see on the three-dimensional stress state, dynamic stress state, and see whether you can use some critical plane approach or something in order to correlate between single wire testing and the full conductor behavior. But we just concluded that looking into all the longitudinal axial stresses, taking the imperfections into account, it was not possible to further correlate it to what we see on the full conductor testing.
Okay, many thanks. But just a little more questions. Is the tension is important? Is the tension plus the bending is important for the conductor fatigue, or just the bending is important?
Yeah, also I guess the tension will set up the initial condition with respect to friction, because in our model we included the geometrical imperfections and also the friction that will be introduced if you have put, because the conductor will have some tension. So since it has some tension, you also have friction between each layer of wires, contributing to some friction stress. And actually, it is quite significant with respect to looking at realistic curvature and whether you are in the stick regime or not. At least for the innermost layers of the wires, that is the stick condition is quite relevant. And that is, of course, relies on how much tension that you have in the system, and also the extrusion of that whatever you have on outside of this conductor also plays a role there, of course. So, so I think, yeah.
This picture is showing that we can apply tension and a certain curvature. We can change the curvature with some contacting surface. This then monitor the curvature, and at the same time you need to apply tension in the test rig. I just enlarged this picture showing the test setup.
So then there's a lot of questions, of course, that relates to this, because when you put this in operation, then copper will expand something more than the steel, and of course it is the steel hardware that takes put this together, and you might during operation have compression unless you're getting some sliding and some thermomechanical interaction, and then you might have a situation where you gradually build up more tension in this copper conductor, and so it's quite complex. So yes, the axial force plays a role. How much in operation? Well, that is a complex question actually to answer.
And another issue is that because all the current testings, they are testing in one plane, either full scale or this component level. But actually, the power cable, they are not bending in one plane. They are at least like rotating, right? Under the connection point. It's like this. So we are also thinking about developing new testing procedure to perform the, for example, conductor level testing, not only in one plane, but considering the real situation of the bend stiffener. Within the bend stiffener, you are rotating actually around the handling point. And then
you will have also you will have both cases. You will have both the rotation and you will also have in plane. So you will have a kind of a chaotic behavior in reality. So then traditionally in industry, to speed up the fatigue test, you will use rotative testing, and that is very efficient, but then all the points in the cross section go through the same relative displacement, so you are not less exposed to fretting effects because you are in the sliding regime, and then you have more wear issue than you're having fretting issue. But whereas if you have in plane, then you would have fretting points on the tensile and compressive side of the cross section of the wire, which then might then trigger initiation of cracks from the surface. So it's totally depend on the loading condition.
I recommend that we have a specific mini workshop on the fatigue of copper conductors. That will be very interesting.
Yeah.
Let's focus on that one topic. I think Lingwan and Orient, you can use this academician workstation to organize that, a specific topic on fatigue of conductors. That will be then we have more time to discuss.
Yeah, Dr. Yi, actually there are two more questions. Maybe you can give a quick answer to that. Okay, the first one is from Chris Sherman from DME. I wonder who pays for the testing. Is it paid by the cable manufacturer as part of their cost of product development, or should it be borne by a project as part of a project-specific type testing? And what is the rough order of magnitude of a test package for a project? It's in the Zoom chat box. You can check on that.
I think eventually we pay the bill because we use the power. But normally, if you look at the practice, I think the operators and the manufacturers, they have a deal how to share the cost on testings. If it is a development project, maybe a manufacturer will cover more. But if it is project, I think the project will cover more. And the magnitude of this full-scale testing for typical I'm not saying 1 year, but 3 to 4 months full-scale testing, it will be around, I would say around 3 million Norwegian krone. Yeah, for full qualification testing.
There's another question from NBO. For static cable, what is the allowable level of strain induced on copper conductor?
Can you just repeat what is
okay,
the strain allowed the strain level? You mean?
What is the allowable level of strain level induced on copper conductor?
Of course, you cannot exceed the limit, elastic limit. But if you are under this balance control, you can allow more.
Maybe we ask in other way. Is it allowable for copper conductor to exceed yielding strength?
Ask DNV.
Okay. Yeah, this is about the approval procedure, I think.
Niels, you answer this question.
Yeah, I'm happy to answer that. The problem is that there is, say, the acceptance criteria for allowable stresses and strains. So these different components is very scattered, and I'm not aware of any, say, specific requirements giving in standard, because it's very, say, manufacturing specific how you manufacture the core, how it's compacted, and so there you will not find any specific limit in design codes that I am aware of, at least not DNV codes.
Yeah,
I think at this level, testing is very important. If you are sure that your product under that strain level will not fail, I think DNV will not reject to approve your product.
No, it's about how you qualify the product.
Right, yeah.
There has been a common industry practice of 0.15%, right? That has kind of a number that has been popping up. 0.15% maximum strain in copper. That has been kind of at least a number that I have heard, but I've not seen that it in some standard. But I just came into this 0.15% for many projects.
Yeah, we are asking this mainly because that we, according to our practice in the projects, that copper is very easy to access the yield strength during the operation or during the installation phase. If the water depth is too large, it's very easy to access this, and this is caused a large problem during our design of the cable. And for example, like for water depths exceed 1,000 meters, the yield strength of the strain of the copper will be very large. But during our testing, and some kind of the strength will not cause damage to the copper, because the copper has a large elastic level or kind of like this according to its characteristic. So we are imagining whether it's possible to access the yield strength and not still maintain the plastic level. Yeah.
Dr. Ye, would you like to comment on that, or?
Yeah, as I mentioned, you find some industrial practice, but from the classification society point of view, I think you need to go through the qualification process anyway. And of course, if you look at the flexibilizer development process, many times the practice goes beyond the classification rules. And then you need to convince the operator that you are operate safely. That is, eventually you need to meet that safety issue. Even though you operate, and then you can demonstrate that your criteria can sustain the load in operation. That is very important.
Okay, thank you, Dr. Ye. Since we are running late of the schedule, let's take 5 minutes break. Okay, is that
So
okay
you're
for everyone?
speaking the
Yeah.
break.
5-minute break. Then we come back. And thank you all for your patience and attention. Okay, hello everyone. It's time to continue with our workshop. So the next speaker would be Mr. Junxuan Hu from Power China. Mr. Hu, are you online or not?
Yes, I am.
Okay, thank you. So Mr. Hu is the technical manager of the project of Wanning Floating Wind Farm. So Mr. Hu, the time is yours. Please go ahead, thanks. You can start sharing your screen.
OK，那个不好意思啊，因为我时间比较仓促，没有做这个英文的 PPT，我是做的一个中文的 PPT，所以我先共享一下。
中英文 mix 一下啊，你可以把摄像头打开，如果可能的话，方便的话。
好的。可以看到吗？
Presentation in mainly in Chinese, so sorry about that. So yeah, you can continue.
好的，我就直接用中文介绍吧，因为我英语口语也不是很好。那么我的介绍分以下4个部分。第一个是因为我们目前在做了一个海南这边的万宁的漂浮式项目，所以先介绍一下我们这个项目的基本情况。另外一块就是介绍我们这个万宁项目目前这个动态缆的一个设计总体方案。然后第3个是那个我们设计过程中遇到的一些关键性的技术难点。第4个是我简单介绍一下我们中专业的一个情况。那么首先我介绍一下我们这个万宁漂浮式的项目。那么这个项目是位于海南省的那个东南面，离岸距离是22公里，然后平均水深在100米，规划的装机规模是100万的千瓦，然后项目分2期建设。那么1期这是我们这个厂区的一个布局，1期开发在厂区的西南面，就是这里有12台风机，装机规模是200兆瓦。那么首批的话，我们是打算安装6台样机，而且这个项目现在这几天可能陆上部分要开工。这是我们这个项目的一个发电机组。发电机组我们采用的是这个轮毂那个叶轮直径为260米的一个发电机组，单机容量的功率是16兆瓦，然后采用的是这个直驱和半直驱2种技术路线。6台样机里面采用的风机的厂家可能有好几种，就不止，因为它是一个示范性项目，所以没有统一这个风机的厂家。另外的话，我们这个机舱的正常一个加速度是0.3G， 然后运行的最大风机的最大倾角是10度，极限运行的一个最大倾角是15度，正负15度。那么这是我们目前设计的一个基础的一个浮体。浮体分2种形式，一种是 A 型的，一种是 F 型的。然后左边就是 A 型的 ，A 型的是3立柱的，然后这边右边的是 F 型的。那么基础浮体我们的用钢量大概在350吨每兆瓦，然后设计环境采用的是50年一遇的风浪流荷载。那么下面介绍一下我们这个细薄链的布置方式，我们是采用的这种悬链线细薄系统。3种细薄链布置方式，我们现在研究的是有3种方案，一个是3×3的，另外一个是2×3加1×2的，还有一个是3×2的。那么现阶段我们采用推荐的是中间这个，就是2×3加1×2的。另外根据我们工厂的工程的一个厂址地质条件和那个共享网搏击基础的位置要求以及用期采用的是这个桩铆，这是它的一个布置方案。然后介绍一下我们这个比较关心的动态缆的一个设计，因为这是我们目前动态缆的一个是总体的一个设计方案，采用的是这种 blunt wave 的波形，相当于是从风机这里出来之后，采用一个波高，然后下来之后通过中间接好，再接到静态缆。因为我们这边一期工程我们没有建海上升压站， 所以也不存在这个漂浮式海中放电升压站和那个内容，所以我们是采用的这静态缆直接拉到岸上去。这个电等级是66千伏。那么首先我们看一下这个动态缆的定义，这一块应该大家都是比较熟悉了。动态缆和那个静态缆还是有一些区别。动态缆的区别主要是说，第一个是这个动态缆2层以上的偶数层的一个凯装，然后另外的话，第二个是动态缆凯装不与海水接触，然后另外的话，动态缆有统包内外层的披护套，然后还有一个铜带和同时屏蔽的一个屏蔽层。那么第5个是动态缆及其附件有复杂的动力学针对性设计，需要具体的单台风机的一个工况。这个也大家也比较熟悉，就是我动态缆设计的时候，每台风机都是要进行单独设计的。那么动态缆的一些重要指标有5个，一个是满足凯装层的一个扭矩平衡要求，第二个是满足凯装层承载80%轴向拉伸的荷载，第3个是满足这个净重比要求，第4是满足径向阻水要求，第5个是满足至少25年服役期使用的寿命。那么这是动态缆的一个本体设计。动态缆的本体设计主要是2个方面的一个困难，一个是就是由于风浪流浮体等多重动态荷载作用，使得动态缆承受了拉伸、弯曲、扭转、振动等交变荷载，其综合的力学分析比较复杂，所以我们现在需要建立一个风机浮体到系统到动态电缆到的一体化的一个仿真模型。那么同时因为它这个比较严格的工况，所以动态缆也是一个力电磁热等多物理场耦合的一个多耦合的一个场景，所以导致我们现在这个动态电缆的一个仿真软件分析还是比较复杂。那这是我们目前在做的一个动态缆的一个线性设计。那么我们动态缆的线性设计的首先是一个输入条件的介绍。那么输入条件有以下6个，第一个是我们这个浮体的一个偏移量，就是上下前后上下的一个摇摆。第二个是我们一个海洋环境的一些条件，比如说比较关键的一个水深、波浪还有洋流。第3个是海生物的附着的情况，因为这个附着的情况也是根据地理位置的不同而不同。然后第4个是我们的土壤的地质的条件。第5个是周围铆系的结构，因为动态缆要避免与这个铆链的一个干涉，包括比如有的地方还有一些输油的软管，这也是需要进行一个避开的。那么第6个就是我们动态海缆的一个结构参数，这个仿真软件里面会输入这么一些条件。那么输出的一些条件也是有总结下来有以下6个。第一个是静态条件下线性的一个布置，就是我们针对这种工况，比如说水深，我们最适用的一种线型是什么？另外的是附件的一些基本要求，因为这个附件包括有这个弯曲加强件、浮力块、配重块、海床固定，还有防磨件等等，所以对他们也提出了一些力学和物理学的一些参数要求。那么第3个是极限荷载与力学性能的校验，也就是说对我们这个载荷拉力、弯曲半径等等进行一个在这个软件里面进行一个校验。第4个是疲劳寿命。第5个是动态缆与浮式结构的安装角度。这个安装角度，也就是说我动态缆和我这个浮体怎么样一种连接方式或者什么位置是最优的，这也是在这个仿真软件和这个动态缆线型设计的时候要确定的。那么第6个就是我们的安装方案，也是指导我们后期的一个施工。那么这里有一个我们动态电缆整体的一个，我这个 PP 老是跳，整体的一个那个设计流程。那么首先就是我设计那个动态缆的一个本体，这一块可能很大 的一个工作量是我们像东方啊厂家来执行的。第一个是电单元和光单元的一个设计，然后另外是截面的一个加强设计，还有就是那个机械力学仿真分析，还有多物理场景的那个仿真分析。这里包括比如说我们现在的单机容量是16兆瓦及以上的，那么还是66千伏的，所以就涉及到这些截面啊，还有那个电学性能的一些设计。那么另外的一个比较大的工作量就是说，我动态缆设计出来之后，我线型也仿真出来了，那么我就是有一个迭代的过程。根据刚刚提到的，就是我把这个工况，就是我比如说风浪流等一些所有的参数输进去之后，我第一次设计的这个东西，我会根据这个建立的模型，首先在里面建了模型之后，我会根据这些工况条件进行一个仿真，然后反过来看它的运行效果，反过来修改我们这个整个线型的设计，包括整体的设计。就是我首先把这个第一次设计好的东西输进去之后，反过来进行一个迭代。这个迭代反过来修改的不只是我的线型和附件或者其他的，我们会对这个动态缆的一个本体，就是我这个整体，比如说我那个结构啊、截面啊，进行一个调整，然后再反过来对我们输入这个仿真模型，再进行一个仿真，这样来回的一个迭代过程，所以达到一个不能说最优，就是一个接近最优值的一个效果。这就是我们这个整个动态电缆的一个整体的设计流程。那么我们在做这个工作的时候遇到了不少的问题，现在我介绍一下。第一个是这个接线方案的一个确定，因为我们在做这个方案的时候，因为我们这个目前的话就是说有2种比较成熟的也是用的比较多的一种方案吧。第一个是我们这个链型的方案，就是一台接一台，这个大家一说也比较熟悉。我这里是4台的话，我就是一台接一台这样连过去。那么第二种就是我们这种新型的布置，我4台风机通过一个集线器一起送出。那么这里面这个我们可以看得出来啊，就是从这个图片就可以看得出来，我们这个新型方案是有很多优点的。第一个是我这个因为集到集线器之后啊，我们这个动态缆这一段就比较少了，比这个一条接一条的这种方案就肯定是至少是少了。除了终端风机之后，其他都是只有一半，对吧？另外的话，我就是说我这样设计之后，比如说根据风机的布置，2排的话，我这个静态缆是可以布置在中间，然后两边的动态缆分别往这个集线器这里拉过来之后，那么我就减少了这个动态缆与这个铆链啊，还有包括其他一些东西的一些干涉，所以这个是比较方便的，也方便我们以后动态缆的一个布置啊，对设计和施工都是非常简单的。那么这里有一个难点，就是说我们现在这个集线器，一个是它这个电压等级也比较高，目前国外的话有应用的只有15千伏，它可以用到24千伏，但是用的很少，而且只能进口，它的可靠性有待检验。另外一个就是这个集线器啊，如果不可靠的话，那么我只要这里出问题，那么整条这个集电线路所有的风机都发不了电，而且这个集线器出问题之后啊，它的检修啊和那个运维是非常麻烦的。因为这里我们也找国内的一些厂家，进行了一个设计，包括像国内做的比较好的那个长南电工啊等等，找他们也设计了这么一个集线器，结果做出来的那个体积和重量是非常非常庞大和巨大的，而且最后考虑它的施工啊也是非常麻烦的，所以这里这个东西就是设备上啊，这个集线器的设备啊还有一定还是需要一个技术攻关的。 这是这一点，就是我们节俭方案的一个缺点。那么第二个是我们在设计过程中啊，还有一个就是关键时效，有这么一些难点，总共我这里总结了6点。第一个是就是关键时效位置在于这个防弯器端部浮筒段触地点，应该对关键位置进行一个严格的控制。也就是说，我这些地方是后面风机运行25年最容易出现问题的地方。这主要也是我们这个动态缆附件，相对这是几个关键点，所以说这里一定要注意。另外一个就是设计迭代过程的一个比较复杂，就是刚刚提到的，我在仿真的过程中啊，动态缆本体设计了之后要仿真之后反过来修改这个动态缆的本身，所以这是一个比较繁杂的过程，而且也是比较费时。另外的话就是说我每个项目每台风机的机位点的工况都不一样，那么就是说我在这个发电厂设计的施工之前啊，就要做大量的一个设计工作。就是这也是我们目前这个说针对我这种固定式的风机的一个非常本质的区别啊，是没有一套通用的理论和设计手册，没有个这种通用的规范来约束它。那么第三个是说到这个规范，因为目前的话，我们动态缆这一块的规范很多是引用这个油气平台里面的那个电缆的规范过来的，所以很多规范是缺失的。而且我们现在这个电压等级啊，升到了66千伏，后期也不排除到110千伏等等。因为我们目前这个项目还是1级20万，后期的话肯定是还上升压站的，还有80万。那么也就是说，我80万的话，到时候会用到这个220千伏的动态缆，所以这一块的话，所有的设计规范目前还是缺失的。那么我现在在设计的时候，我设计的安全运度测试工况，包括加速积劳试验的标准和结果的评估等，都存在一些不确定性，所以这一块也是需要完善的。那么第4个就是我们在设计过程中需要考虑这个附件安装的友好性。因为根据我们目前几个示范项目的了解啊，就是说我们这个动态缆的安装，就是这个动态缆与浮体的固定这一块的位置，都在水下。那么在水下的话，它就不友好了。为什么？就是说我这边一般这些地方流速都比较大，如果有水下这个动态缆这个防弯器要怼到这个浮体里面，那么是必须由人下去进行施工。那么流速大的话，那么施工窗口期是非常短的，所以有时候非常受制约。所以我们在思考，就是说我这个连接部位怎么处理？一是要避免这个水下施工，另外的话，我要保证它这个安全的可靠，包括我这里到底是不是采用接线管，还是说直接冲到里面去，包括还有那个浮体里面和外面的这个水环境和里面的那个防水措施等等，都是需要考虑的。所以我们目前的原则就是说，我们这个项目目前这一块设计的原则就是说，杜绝这个水下施工。另外第5个是这个动态缆的一个线性的监测。那么线性监测的话，我们设计的这个 plant wave 的波形设计出来之后，那么我后期运行25年，那个时间还是比较长的。我怎么来监测这个那个线性还是保持这个状态呢？包括我们南海这边，它的那个海生物的附着啊，也是繁殖是非常快的，所以这个海缆监测这一块也是一个很大的问题。包括这个监测设备的选取啊，传感器的选取啊，它的那个取电啊，还有那个后期的运维啊等等啊，这些都是一个难点。那么最后一个就是说，我设计过程中要考虑现行的那个海生物的附着和后期的运维， 那么我这些浮力块以后，如果是海生物已经附着了，那么我到底是清除还是不清除，或者说我25年它还能不能浮起来，这也是需要解决的问题。所以总的来说，有这么一些难点吧，是目前我们在设计过程中遇到的，可能后面不断随着那个设计的深入啊，会不断的发现更多的问题。那么这是这一块设计中存在的难点。那么最后我简单介绍一下我们中农院的一个情况。那么我们中农院的话是有70多年的历史了，因为的话我们是属于这个中国电建，地理位置是在长沙。那么我们现在是有那个设计勘察、咨询和监理4中甲，海洋工程的勘察师以及电力总承包师1级，获得了很多奖项。然后另外这是我们的业务啊，业务板块有技术服务，还有工程承包、投资运行。我们的行业有水电新能源、水利与环境、城乡建设。我们这边人力资源还是比较强的。第一个是我们培养了2位院士，还有5位勘察设计大师。然后最近招的人基本上都是985的硕士。也就是我们的一个核心优势有产业链多行业、投资、融资、科研、人才和信息化的一个优势。那么这是我们做的一些海上房地的规划。我们在辽宁做了这个营考的海上房地规划，然后在河北和唐山市做了14.5的一个海上房地规划，在山东做了那个海上房地的规划，还有一些中石油一些公司的一些海上房地的规划。那么还有我们在广东有一个汕头那边有几个项目。那么这位剩下就是广西和海南，海南这一块也是我们做的海上房地的规划。好的，我的汇报完毕，谢谢各位。
Okay, thank you, Mr. Hu, for your interesting presentation. You have presented many practical challenges faced during the installation of the wind farm. Okay, now it's a Q&A session. Any questions from the audience? Any questions? If there's no questions, then we can move to the next presentation, which will be presented by Prof. Shi Xiaofu from Shanghai Jiao Tong University. Prof. Fu is a distinguished professor at Shanghai Jiao Tong University. Meanwhile, he is also the adjunct professor at NTNU. His main research area include vortex-induced vibration of flexible risers and cables, hydroelasticity of very large floating structures, such as floating bridges, ships, floating airport, submerged floating tunnel, and also hydroelasticity of large aquaculture structures. In addition, he's also an expert on the hybrid model testing. Okay, Prof. Fu, hand over to
曾
you.
总看一下，曾总看一下，我这里根本来不及了。
Prof. Fu, you can start sharing your screen.
喂，顾总。顾总。哎。喂，顾总。
Prof. Fu, can you hear us?
Hello, can you hear me?
Yes, yes, you can start sharing your screen.
Okay, now it's okay. Can you see it?
It is ongoing, still sharing, but we cannot see your screen yet.
We see a black.
Oh. Something wrong with the software. It's Can you see it?
Are you sharing the application or screen?
Are you using 2 screens or just 1 screen? Prof. Fu, maybe you can quit Zoom and log in the Zoom again to try for another time. Okay, I think there's small technical issues faced by.
Hello?
Yeah, you can start sharing your screen again. Let's check.
So once I share my screen, it will be stopped. I will try again.
Still the same issue.
Can you see it? No?
It's a black screen, so we cannot see the content.
It's very strange. So I had to, you can move. Yes, Professor Wan, you can move to the next speaker. I will change
okay,
another.
Okay, all right. Let's move to the next one first.
Yeah.
Okay, the next speaker is Prof. Jun Yan from Dalian University of Technology. Prof. Yan is a professor of computational mechanics at Dalian University of Technology, and he's also the Changjiang Distinguished Professor, serves as the vice chairman of Liaoning Mechanical Society, and is a member of the Foreign Exchange and Cooperation Committee of the Chinese Mechanical Society. He received his PhD degree from Dalian University of Technology. Now he's a vice head of Department of Engineering Mechanics of DLUT. And Prof. Yan specializes in the field of structural and multidisciplinary optimization design and structural design and testing of umbilical and flexible risers in offshore engineering. He also devotes to the application of artificial intelligence technology to ocean engineering. Okay, Prof. Yan, are you online? You can start sharing your screen.
Just give me minutes.
Okay, no problem.
So can you
yes,
see me?
Yes, we can see your screen.
Okay, I will begin. Yeah.
Thanks.
Okay, thank you. Many thanks for the invitation from the academic workshop workstation. I'm Jun Yan from Dalian University of Technology, and the title of my presentation today is innovative design and experimental verification of marine cable structures. And this work, I think, is collaborated very closely with Swing Savic and Dr. Nai Chunye and Hong Guo from the Zhonghaiyou, and Chen Kai is from the NBO. And so I will begin my presentation. And this is the outline of today's talk. And first is the background and motivation. And from the column, we can see that the China energy consume is developing very quickly, and we can see the shortage of the energy in the land of China. So the developing offshore oil and gas is a major energy strategy in today's world, including China. And the umbilical cable is one of the key equipment for energy transmission and production control, and is known as a lifeline in the marine energy development. And if we see the South Sea in China, we can see the state is very severe, and this kind of severe sea state generally requires very high performance of umbilical cables, and the umbilical is flexible composite structure with a large slenderness ratio, whose failure mode is special, and the design optimization is very complex. And here we can see some how to what is the meaning of the high performance. We can see for the stiffness application in the in the North Sea, in the South Sea of China, the water depth will exceed 2,000 meters, and the internal pressure more than 30 megapascal. And at the same time, the flexibility, such as the bending radius, is less than 2 meters, and the physical life generally requires larger than 25 years. And also we have very high quality performance requirements for the electronic properties. And so Chinese marine cable urgently needs to develop towards high performance. And so this is why we carry out the research about the multidisciplinary optimization design of cross-section layout of umbilical cables. And from the left column, we can see that for umbilical cable, normally we need compliant structures and multi-functional collaboration between the electronic and mechanical functions. And also we require the reliable over long terms of the cables. But if we look at the structure of the umbilical equipments, we can see normally we have a lot of function components such as cables, optical fiber cables, and steel pipes. And also we have a lot of stiffening components such as populate the widget and armored steel wire and inner and outer sheaths, and how to arrange the function components and stiffen the structures is the challenge. And if we check the specification of the designing process, such as the ISO specification, it requires the cross section should be compact and symmetrical as possible. But there is no clear operation method for how to define symmetry and the compactness. And this is one challenge. And another is actually we face a lot of layout design results, such as for the first row of the design, if we put one steel tube in the central part, and we totally have 56 possibilities of the layout. And if we put 3 electronic cables in the central part, we have another 28 possibilities. And in engineering practice, there is a huge challenge of the incompatibilities. And also I caught up in the design paradox of one over the other. So how to cope with this kind of difficulties? We just introduce some optimization method or optimization model into the design process of the umbilical cross section layout. And the right column is optimization formulas, and the left part is the explanation. And first, for optimization model, we 3 key parts. The first part is the design variables. That is the geometric center coordinates of the components. And for the objective functions, in our model, we consider three functions. The first is the compactness. That is minimize the envelope of the circle radius. And the second function is the symmetrical balance. We just introduce the virtual gravity G into the formula, and based on the tensile stiffness. And the third function is the heat dissipation, the average distance of the heat source dt, and the surrounding area S is chosen as the index to describe the heat dissipation performance. And for the constraints, the components neither overlap nor are the outside the outer loop of the layout. So the right part is the formulas, and but it's a very hard problem to solve the optimization problem due to it's a NP hard problem, and also it's very hard to find the global optimal one. So we just introduce the PSO method, which is it is a very powerful tools to deal with multi-objective optimization problems or highly nonlinear problems. And this is some very brief introduction of the PSO method. And let's check a case study. For the case study, we have 6 steel tubes and 3 cables and 1 fiber optical cables. And from the for altogether we have 3 functions. So that is a typical multi functional problems, and we give different layout design. And layout 1, layout 2, and layout 3. And for the layout 1, we can see for the layout 3, we can see its compactness index is very good one, and its radius is slow, is a small one, and the balance is a very good index, and symmetrical is they have 3 symmetrical axes. And for the sectional thermal field distribution, we can see maybe the layout 2 is the best one, but layout 3 performance is also good one. So generally we choose the layout 3 as the final design, and according to the layout design, we carry out the detailed mechanical analysis of the structures, and then manufactured the umbilicals with in the NBO, and then it is also get some succeed in the engineering. And the second part is the configuration design and intelligent optimization of umbilical cables. Actually, some oil spill accidents was caused by some oil companies in Bohai Sea in 2022. It's in 2011, resulting in the seawater pollution and economic loss due to the rupture of the excessive oil recovery procedure in the formation. It is necessary to design an oil spill recovery system to recover the spoiled oil from the surface. The task is temporary and urgent.
Prof. Yan, we cannot hear you.
Just
so is the connection unstable?
Can you hear me now?
Now we can hear you. So it just
yeah. The connection is yeah. The connection is a little not
yeah, it's okay. You can continue now.
Professor Wang?
Yeah, it seems like the connection is not very stable on your side. So
is it okay now?
Yeah, now we can hear you. So you can start.
So I will try. Is it okay?
Yeah, we can hear you. You can continue.
Is it okay? Okay. So test 1, the umbilical cable structure is more nonlinear. and the dynamic amplify effect is more efficient, and there are a lot of many failure modes. The challenge 2 is the configuration design requires much dynamic time domain analysis with large design space but very small feasible domains. So we just introduce some so we just introduce the optimization method to replace the manual trial calculation methodology, and we just use the RBF surrogate model to replace the expensive time domain analysis. And then the main process is sampling and build a surrogate model, and we give the model validation, and all R square value are greater than 0.9. And with the help of the we just use the hybrid optimization method. In the step 1, the multi-island GA method is used to search for the global optimal design. And in the step 2, the gradient-based classed algorithm NLPQL is used to search the global optimal. And the advantage of the hybrid optimization it lies to efficiently to find the global optimal solution. And from this figure, we can see even though all the sampling solution avoided was a allowable curvature, but with the help of the optimization algorithms, we can find the optimized design. The green point is less than the allowable curvature. So actually, it's succeed to cope with engineering problems. And the first part is actually a lot of integrated testing platform is built for the umbilical cables in DUT, and over 15 sets of the thermal field and mechanical field and electronic field integrated measurement equipments are development in my universities, and also put forward the fatigue testing design series and establish the normalized fatigue condition selection process and criteria. This kind of research is carried out and established the experimental series of the optimal line type simulation, and put forward the selection criteria of the specified structure with the high reliability. And also its installation condition test is carried out, develop a set of strong power composite umbilical cable installation conditions testing technology combined with the simulation, and predict the crash load on the upper bending sections on the installation to verify the accuracy of the numerical analysis. And also some the testing equipment and experiment procedures of the test results are all certified by ABS and DNV, and the testing system is widely used in China as a third part testing and certification of the umbilical cable products. And also some applications are the research results have been popularized in offshore and oil and gas and offshore wind power and other fields. In the past 3 years, more than 30 related projects are applied, and the achievements are reported by the Chinese People's Daily and the news broadcast, and all the achievements is cooperated closely with Zhonghaiyu and Ningbo Dongfang. And this is a summary. The flexible structure represented by marine umbilical cables is an important new type of marine engineering equipment, which contains a lot of challenging mechanical problems, taking the innovative configuration design of structures and the application of the new composite materials as an opportunity. It provides development space and application for structure mechanics and property designs. With the close cooperation with NTNU, especially from with Professor Savik, and also with Dr. Ye, the research on key scientific and technical issues will certainly provide a strong theoretical and support and equipment breakthrough for the innovation of the marine structures. And thank you. Any questions or comments? Yeah.
Thank you, Prof. Yan, for your interesting presentation. Is there any questions? Any questions from Zoom and from Weizhan? Okay, if there's no questions, then we may proceed to the next speaker. Since Prof. Shi Xiaofu, due to some technical issues, Mr. Shi Luhao will share his presentation. Okay. Meanwhile, Prof. Shi Xiaofu will give the presentation. Prof. Fu, go ahead, please. Thank you.
Yes. Thank you, Professor Wan. Yes, it's very glad to be invited.
Sorry for interruption. Please stick to the time schedule because I see you have 53 slides.
Okay.
Yeah.
Not done in March. Okay.
Yeah. Thank you. Thank
you.
you.
Thank you. Can you? Okay, Shi Luhao, can you make it to be in a?
Make it full screen.
Presentation form. Yes. Okay, I can control it, right? No, Shi Luhao can control it.
Yeah, you make it full screen.
Yes. Can you do that?
Maybe he's trying it again.
I think that if
okay.
Yes. Okay.
Yeah.
Thank you. Thank you. Thank you for your introduction, Professor Wan. I'm Shi Xiaofu from Jiaotong University and have been working with my Norwegian friends long time, especially Professor Togi and Suvin and Nanquan and so on. So, my topic will be about vortex-induced vibration of flexible pipes. Next slide. So as mentioned by Professor Suvin Savik and our Yanjun and our other professors, you mentioned about the floating body motions responses. And also we have risers and the cables in the water. So my main research area is about the pipes or flexible power cable, the dynamics responses with mainly focus on the vortex-induced vibrations. So then I will introduce my slide 2. I will introduce my research works in that more than 10 years. Please go to next slide. So I will introduce my experimental research works about VLV. And then I will go to the hydrodynamics of VLV, especially from reverse identification of the flexible pipe experiment. And then I will introduce the prediction method about VLV. And then I will introduce the apparatus and the facilities in Jiaotong University. So the first experiment we cooperated with, next slide, please, is the, yes, click. So, and click, and this model testing is about the heel motion induced vibration. And this project is supported by Statoil, Equinor, and also Research Foundation of China, and we collaborated with Syntef Ocean at MIT. So we were focusing on the heel motion induced VLV on the segment bottom touchdown zone about the vibration of these risers. So please click on 2 times, click, yes, one more. So from here we can clearly see that from here we can clearly see that the purely heave motion will induce the very large laterally out of plane VRV, and this VRV is clearly observed in the sea in the bottom at the sea. You can see in the left side in this camera. And the next slide. And by these experiment operators, we are also looking into, because lazy wave sometimes could reduce the motions. So we also investigated into the heave motion induced VRV on the lazy wave shape. See, we also can clearly see the VRV induced by motions. So this project was we cooperated with Surflum, and also we were doing the motion-induced VRV of the water intake risers. These water intake risers could be for the cooling down of air intake, or nowadays we are talking about the deep sea mine system. So we finished this project with SPM, and we find very clearly, we could very clearly see the motion-induced VRV and the hinges of the hydrodynamics coefficient along the pipe under the heave motion is not anymore. CD is not 1.0 or CM is not 1.2 anymore. So it will be greatly changed. So next one. So we can see that the heave motion induced VRV, it will induce very large fatigue damage. This damage is sometimes 40 times larger than the current induced VRV, and also very large, much larger than the global dynamic caused vessel fatigue damage. So it's very large one for the heave motion induced VRV. Yes, next one. And to understand the mechanism behind we did the oscillation test, we cut 1 4 meters pipe and oscillate in the water with different Kc number and velocity. So we want to understand how the Kc number and reduced velocity control the VRV in the oscillator flow. So we are trying to do this for the prediction actually. So next slide. So here is our previous Swiss and our previous slides. You show the pipes or cables with the buoyancy. So normally it's very hard to decide how much coefficient, I mean the CD, CM, or the lift coefficient applied on the buoyancy and the bare pipe, and how to do the hydrodynamic analysis. So we were trying to get this VRV and hydrodynamic coefficient on them. Yes, next slide. In oscillator flow. And then we can clearly see that in oscillator flow, the strength cannot work very well. It can only reduce the vibration by sometime only 30%. So as we know today, we are thinking about use the variance in the wave affecting zone, and we are not using stress. So it's very clearly, we published this result about 5 years ago. At that time, we noticed that in oscillator flow, the stress cannot reduce the VRV actually. So and still. Yes, today we are still working on this. Yes, next slide. So this is, we also get some stress, the drag coefficient of the stress in different Kc number. And yes, this will be very helpful for the global dynamic analysis. You see, sometimes the CD could be up to 7, and normally it could be about 2.0. So anyway, it's different from the from the uniform flows or stable flows. Yes. Next slide. And also we can get some CM and again, it's different. Yes, next slide. So another issue in China, in South China Sea is the internal waves. The internal waves, the first or the second mode is like that. In the upper one, we have we have the flow like this, and in the down one, lower part, we have the current in another direction. So when we want to know the VRV in this current condition, what's the VRV and how to predict it. So we performed the model testing in our ocean basin. Next slide. So this is the apparatus. We rotate this rig in the water and we put our model here. So then you can get the VRV on the pipes with fiber sensors. So you see it's rotating in the water and the diameter is around 10 meters, and we can clearly see the VRV of the pipes in the VRV. Yes, next one. So again, we can see that yes, this is 2-3 pipes vibration. They are interaction each other, and also we have some tracks on it, and we want to know, the tracks separation efficiency compared to paired one, and we also are investigating the multi-risers interactions and VRV programs by the wakes of the risers. Yes, next one. Yes, next one. Yes, next one. And we also have done some rotating model testing in shared flow. This was done about 10 years ago. I think you have already know this one. This was rotating in our ocean basin. The diameter of this rotating rig is about 20 meters. So we can have this pipe in the water and we measure the vibration on the pipe. Yes, next one. And also we have the drilling risers or patient leg VRV programs, and we have double risers, 3 risers, and 4 risers interactions. We perform this model testing in the ocean basin. Yes, next one. Yes, next one. Yeah, now that's the experiment so far we have done, and it's anyway we are still looking into the experimental results, trying to understand the mechanism behind, and trying to get the hydrodynamics coefficient from this result. And as we know today, we are using the hydrodynamic coefficient like this. We are trying to force the rigid cylinder to oscillate in the water and get the forces on them. But in reality, the risers is vibrating like this, so it's long and flexible. So they are, actually, they cannot be equivalented. So in reality, the risers is vibrating and they are affecting each other for the segment. So we want to know how far away we are to know the coefficient. So next slide. And then we developed the identification method inverse analysis for this flexible riser vibration, and we use the measured string signal during the vibration, and then we use the finite element method. We get the forces on each element, and by least square method, we can easily get the CE hydrodynamic coefficient on the pipes under VRV conditions. Yes, next one. So we validated our method by comparing the result with Vivana, because with Vivana we can easily get the VRV responses, and Vivana inside it has its only coefficient database. So if we can inverse from the response, VLV response, we inverse it, and we can try to get the coefficient, and we compare the coefficient used inside of the V1, then we will know our inverse analysis, whether it's correct or not. Yes, next slide. So this is the inverse analysis. So we can see the CE, the exciting coefficient, is pretty much the same as V1. We inversed the blue one from the V1 displacement response, the coefficient, and the red one was from the V1, because we can go inside the V1 and get the coefficient after the iteration balanced. So, and also CE, also the same. It's very similar. I think it's accurate enough for us to understand the hydrodynamic coefficient. Yes, next one. And we also understand that we were trying to get the VLV and the hydrodynamic coefficient with the pipe with the buoyancy modules. Yes, next one. And we find that sometimes the CA sometimes goes up to 17, and sometimes it's 80. So it's very different from number 2, right? So it could be 17 or 80. So we decided to do the model 13. Next slide, please. So around 2017, we performed the model 13 in ocean basin of Sintef. By a small model like this one is 1 meter length, and we try to understand the hydrodynamic coefficient on this buoyancy module at the bare pipe. Yes, next one. And we get the coefficient like this, CA like this here. This is measured. This is what we measure. We identified from the long flexible pipe. It's like this. Anyway, it's different from our 1. Normally we use CE as 1, and anyway the forced motion. This is from model 13, and this one is today we are using in our software. And here the red one was the identified values. Anyway, they are in the same level. Okay, next one. And here the heel motion induced VLV, we could clearly see it, and we want to know the coefficient applied on it. So we tried to do the inverse analysis on this motion induced VLV to get the hydrodynamic coefficient. Next slide. Yes, this one is the straight pipe in oscillator flow. We get the hydrodynamic coefficient with different reduced velocity at the gamma defined like this. And also we get the hydrodynamic coefficient of SCR under vessel motion with different gamma and reduced velocity. Yes, next one. So the prediction method, and yes, today we are using this kind of coefficient map everywhere, which was done by Gopalakrishnan at 1993. So we were trying to update the coefficient, and that's one. And fortunately, we developed another prediction method model. We are using the so-called energy balancing method to get the VLV response by calculating the energy at each frequency or time step. So sometimes it's very time consuming or it's not converged. So in our method, it's very simple. We just solve the we just trying to find the crossing point between one straight line and one curved line. So you can always easily find this crossing point. So we just with one very simple idea that we use the total hydrodynamic forces equal to the structural damping force. So then we can simply simplify the equations into two. one is the model hydrodynamic equation, another is a model structure equation. So for these two equations, they should be the same. So we can find this crossing point, then we can easily find the VOV response. Next one. So with this method, we have performed thousands of cases that to compare with the traditional software such as 7.7, Share 7. This is one example that we did the response analysis in frequency domain. So we compared thousands of cases. They are always the errors is around 0.1%. So anyway, it's very good for time for both for straight and for SCR in uniform shared flow and so on. Yes, next one. And also we extended this method into time domain analysis. Next one. Next one. And also we compared with our time domain simulation with our experimental results. We have a very good agreement and so on. Next one. So we developed our own software together with the CNOC. So this project was supported by CNOC to develop the softwares for them. And this is our software. We can do both static, frequency domain, and time domain analysis. We can put process, including the frequency domain fatigue analysis, time domain fatigue analysis, and the result plotting. So next slide. This is the softwares. Yes, next slide. And we can also include the stress and the buoyancy modules and so on. Yes, next slide. Next slide. So we were asked to do the comparison between the real design of South China Sea, a platform in South China, and we were doing the fatigue analysis. We were doing our self result, and then CNOC compared with the ones from SPM did by Share 7. So you can see that the error is still very small. So these cases were for steel catenary risers VOV analysis. Yes, next one. So then I will go to the last one for facilities. In Shanjiaotong, we have the facilities like this. The ocean basin is 50 meters by 40 meters with 10 meters in depth, and the deep pit is about 40 meters. This is the ocean basin. And the tying tank, next slide. The tying tank is about 30 meters in length and 16 meters in breadth, and also 7.5 meters in depth. Next one. This is VOV of riser under vessel motion. We have this apparatus. We can simulate the 3 degrees of freedoms for the platform motions, and then we can also measure the VOV on the flexible pipe in the tying tank. That means we can do lots of things by this. We can also do the forced oscillation test. Yes, next one. And this is the internal wave testing rig. Yes, next one. So this one is very interesting. This is a force feedback control testing rig for high Reynolds number, and as you can see from this video, this one is vibrating freely. It's doing the decay testing. So this one, for this one, we are using the spring by the servomotor control. There was totally no any physical springs, mass, and damping. But actually, we were using the numbers of damping, spring, and stiffness, and damping. We just put into the computer, and then we can do a free decaying test like this. You can see we have performed this model testing in the ocean basin. It's working very well. So this the Reynolds number could be super critical Reynolds number, and today the time limitation I didn't present the results, but anyway, this apparatus was working very well. Yes. So the remarks is that more realistic hydrodynamic coefficients are needed for prediction of VRV. We needed to consider the high Lewis number. We needed to consider the effect of buoyancy modules, Swex variants, and also we need to consider the oscillator flows like waves and internal waves. And also we needed to consider the top motion induced VRV because they are playing very important roles. We should consider the large VRV could be found from experiment, and we need proper numerical models. And we need to consider the component between global dynamics analysis and VRVs. Yes, thank you. That's my presentation.
Thank you, Prof. Fu, for your very interesting presentation. We can see you have done a lot of interesting works on both numerically, on numerical model, on theoretical model, and also on the experimental model. Okay, there is one question for you. How to calculate the VIV of dynamic cable with lots of accessories? This is a very general question, I think.
Yes, for dynamic cables, so we can get the motion as mentioned by Sawik and other professor. Firstly, we needed to get the motion responses of the floating wind turbine. We apply it on the top motions of the cables, and then we do time domain analysis. That's very important because in reality the platform is moving randomly. It's not it's not moving very regularly. It shouldn't be in Francis domain. And also especially in China, the water depth is very shallow, as mentioned by Professor Sawik. Shallow water means in very big waves, all the waters will be moving. The moving with the water will generate the oscillator flow, relatively oscillator flow around the cables. So in that condition, the global dynamic responses will couple with the VRV responses and will totally change the coefficient, hydrodynamic coefficient of the cables. So that will introduce new challenges and design problems. So anyway, this will be very important, especially in China for shallow waters. So yes, that's what I can see.
Thanks. I think Dr. Ye would like to say something.
I have a question about this software. I think I'm very much impressed by your comparison with CR7. Just a very simple question: is this software is a full functionality compared to CR7, or you are still missing some pieces? And is it commercially available, or is only for your own research? I heard about this software before, but this is my first time to see you have extensive comparison with CR7.
Sure. Yeah, very good question. Actually, we have been developing this software for about 5 years. And in the last 3 years, supported by CAOC, we were commercializing this software. And we were asked to do the first job is that we cover all of the functions of the CR7. So in this case, our softwares have covered all of the functions that CR7 could do. So that's the first question, and we are trying to commercialize this. But sometimes it's not easy to do it. We have some special culture tradition, so we are doing this. We are trying to do this. Thank you, Professor.
And also I also see that the software includes the time domain wave analysis. What is the technology readiness level, this TRL level about this time domain? Because I see that I read some paper about this time domain as well. I see that there is still a way to go to validate the time domain wave analysis methodology.
Yes, very important questions. Actually, so far I really trust the methodology developed by Tucson, supervised by Professor Sawik. actually we were trying to use that model, but the differences between our models and Professor Savink or two things method is that we were trying to use the hydrodynamic coefficient identified from our model testing. We were not using the coefficient from the rigid cylinders post-oscillation test or any others. So we were trying to use the one that identified directly from the flexible, risers in VRV. So anyway, for the level, technical level, from my point of view, for this one, because for engineer design, especially for CNOC, they are more focusing on the comparison between our software and others softwares. And from my understanding, that there was no commercialized software in time domain, so we couldn't.
No, that's why I'm asking.
Yeah, so I couldn't push CNOC to compare with no one. So, but CNOC would, they were understanding this condition. So from my point of view, I think this our software is ready to be used, but we needed to do more, validation or comparison, because we have lots of testing cases. We want to compare one by one, and then we can release it. But so far, we compared about 100 cases. They matched very well. So yes, thank you, Professor Yan.
Prof. Yan, Prof. Yanjun, or would you like to say something?
Very good.
It's a very nice work, Professor Fu. A very short question, and where we play very important role in flexible riser and also for marine cables. But which one is more important? Do you have some comments on this issue?
Flexible risers and
marine cables. Okay. Or umbilicals, which one is more important?
Yes.
So have you some comments?
Yeah. From the industry, need, from the industry point of view, they are, they have different applications, and but I think Standard Oil has changed its name into Equinor, right? So that means we are not more focusing on the drilling oil. In the next 20 years, I can see that in China we still need oil, right, from drilling from the sea. But as you said, the cables, the umbilicals, they are becoming more and more important, because for the cables today we are talking about the renewable energy for floating wind turbine, and even for the bottom fixed wind turbine, we still need the cables, and the cable is still have to be dynamic cables. So from my point of view, I think in the future, cables and umbilicals will be more, important. So even it's hard for me to see this, but I had to. That's my understanding. But I'm still working hardly on the risers and others. Yes. Thank you.
Okay. Thank you.
Okay, thank you, Prof, for your excellent presentation. Then we will move to the next speaker, Mr. Lu Haoshi from Orient Cable. Yes, he's a technical manager of this Orient Cable, and he mainly responsible for research and development of umbilical and dynamic cable system. And he's also the leader of 66 kilowatt dynamic cable coupled mechanical, electrical, and thermal fatigue test. Okay, Mr. Shluhao, please go ahead.
Yeah, hello everyone, can you hear me?
Yes, we can hear you.
Yeah, thanks for being invited to this session, and I'm Lu Hao from Orient Cable, and I would like to have a bit introduced about like coupled mechanical, electrical, and thermal fatigue performance evaluation of the dynamic cable, which is one of the topic we just faced with during our experience with the dynamic cable. So here is my brief content of the of this presentation, and so firstly, maybe have a brief glance of the Orient Cable. So Orient Cable is actually a manufacturer of 4 sections of the cable, including the HVAC subsea cable, HVDC subsea cable, land cable, and also the umbilical and dynamic subsea cable. I think today's focus mainly on the dynamic subsea cable, and as the left side, just have a glance and of our manufacturing plant. This is a newly built large manufacturing factory that can provide all of these 4 sections of the products from our factory, and we actually have a lot of achievement already achieved, as I mentioned below. And regarding the dynamic cable, actually, Orient Cable started with the application of dynamic cable from 10 years ago. We have first dynamic cable in 2012, and which is applied in China, southern China Sea zone. And then in the following 10 years, we have applied with more than like 10 projects of the dynamic cable from including the application in Malaysia and also in southern China Sea. And in last year, it's a milestone for us to make implementation of the China's first floating wind project dynamic cable for Three Gorges Group. And also we have just been awarded various of the floating wind dynamic cable like Wenchang project and Lufeng project, and also including some of system like piggyback dynamic cable system. Yeah, actually, so according to this kind of the allocate a lot of experience with the dynamic cable. And just to mention 2 of the most significant projects for us. One of these is as I mentioned, is the China first floating wind dynamic cable project. It's a 35 kV dynamic cable located in a typhoon zone of China. It's in the South China Sea, and the water. One of the important thing to mention here is the water depth is 28 meters. But however, the horizontal drift of this platform reached 30 meters, which is I believe will be quite easy to see through phenomenon in China offshore, because in China coastal, it's most of the region have low water depths, and this region most of them will and this drift caused a large challenge to the dynamic cable design. So as you can see on the right side of the presentation, there is a figure of our configuration design of the dynamic cable. It's a double wave configuration design subject to the weather condition and to allow for a sufficient length of dynamic cable during the large horizontal drift. So actually, it's a milestone for the floating wind. And another one is still a 35 kV dynamic cable, and it's I believe it's first deep water floating wind dynamic cable. It's have offshore distance with 130 kilometers, and the water depths have more than 100 meters. And it's including a dynamic cable system and a piggyback dynamic cable system. It opens a new era to supply the offshore oil and gas development power from the floating wind, just like the new floating wind farm developed in Norway, like called Hywind Tampen. It's both of them would like to supply the power to the oil and gas platform from a floating wind farm. So it's actually I believe it will be a future trend for the development of the floating wind. And as I mentioned, such kind of projects and experience we faced during in this industry, and we do experience a lot of challenges on the dynamic cable. So I would like to mention some of them of these challenges, and this might have some innovative idea for the research area, and might be interested for you. And actually, first to mention is actually the development of the floating wind dynamic cable is actually based on the experience of the oil and the gas industry. As we all know, the oil and the gas industry actually has been very experienced with kind of deep water and medium or low voltage dynamic cable in the previous 20 years. Actually, however, they are actually lack of the knowledge on the shallow water and the high voltage. The reason is mainly because that oil offshore floating platform is normally applied in the deep water condition. However, for the floating wind, especially the commercial floating wind farm, it has different features from the oil and gas dynamic cable. As I listed in the presentation, you can see here, actually for the floating wind dynamic cable, it will be high voltage, large cross section to achieve a large power transmission. And the environment condition is normally in shallow or ultra shallow water, and it needs to connect between the multiple lamps or platforms, compared with only single lamps or single platforms to be connected in the oil and gas industry. And apart from this, I think for a commercial floating wind farm, it will normally include more than like 50 or even more floating turbine. So as you can see, it's there is a figure of a typical floating wind farm. It actually includes more than 80 floating wind turbine, and it's due to locate this floating wind turbine. There it needs to include a large area of the ocean. So it means the floating wind farm, the scale will be very large, and it will include a variety of the water depths, and also will have the complicated seabed condition, like the seabed will including the soil and other kind of the seabed. So in this case, we think in our previous experience, we will face with the challenge on designing and the manufacturing of the dynamic cable. So for the first one would be the configuration design. As I mentioned, there will be a large scale of the zoom to be applied for the floating wing. So it means each of the dynamic cable may face with different environment conditions from different water depths, from different seabed condition. So it requires for a lot of the sensitivity study and extreme analysis to achieve a configuration applicable to the whole wind farm. Because same configuration, a less sensitive configuration can make the design cost to be lower and make a lower verification cost. But the problem here is there is too much sensitivity study to be made for a single lamp of the dynamic cable. So it's cost a lot of engineering works. So what we are facing here is actually to decrease the engineering work during the configuration design, and we are eager for a kind of software to help us to decrease such kind of study or analysis on a platform, so we can easily handle with the configuration design. Yeah, and another question regarding the dynamic cable is the electrical concern. As I mentioned, so for the floating wind dynamic cable, it's the main purpose is to transmit the power from the wind turbine to the land or to the power platform. So it will cause it's a common idea that the electrical concern would be a most important idea of the dynamic cable. So the one of the main failure mode of the electrical cable is the insulation breakdown. And for the dynamic cable, we will normally apply a wet design instead of dry design. I mean, due to the we all know that the lead sheath don't have a good property on the fatigue performance. So for dynamic cable, we will change from the lead sheath to TRXLPE to be the as the insulation layer. So at this case, the electrical performance and combined with the fatigue performance will be one of the most concerned area of the dynamic cable. So during the for current case, API 70E are the one of the standard applied for the dynamic cable and umbilical in the oil and the gas section. But for the floating wind section, I think API 70E seems cannot cover all of this voltage. So it's need to be transferred to the SIGRI 862, which also describe about the full scale fatigue testing. But for these standards, it's still more concerned about the fatigue, mechanical fatigue performance. But we have a question here. Actually, is during the operation of the dynamic cable, actually we are the cable is withstanding both the dynamic motion and in the meantime there is electrical condition and the thermal condition on the cable. So there is a question here is whether they have a coupled effect for these three kind of conditions. I mean the mechanical fatigue, electrical condition, and thermal condition. Whether they have any coupled effect. So according to the standard of it's the newly standard of SIGRI 862. Actually, it's still using a separate electrical type test and the fatigue test. Namely, they are not coupled with the electrical performance with the fatigue performance of the dynamic cable. So actually, what we are thinking about is that whether this will affect the performance of the dynamic cable. And actually, it's an open question. But what the Orient Cable are planning to do is to have a kind of to make a test program regarding the dynamic cable, and to we have set actually 3 tests program. One is like a separate fatigue as an electrical type test, and another one is kind of like make it partly coupled. One of the cable sample will experience with both fatigue test and electrical type test, and another one will experience with the type test, only electrical type test, and then we can compare the of them. And the third one we considered about is like we have a fully coupled test, like to make the type test at the same time with the fatigue test, which will make the most fully coupled of the electrical, thermal, and mechanical loads on the cable, and to see what will perform and what will look like on the cable. Yeah, and we have also actually make a preliminary test setup of the cable, and as you can see, we have our own fatigue test machine, and we are trying to build up a kind of electrical loop on the test machine to make voltage and the current of this cable sample and during the fatigue test. And but it's still open. It's still a preliminary idea of the test. So we are welcome to the researchers to have suggestion on this kind of issues. And finally, regarding to the further research topic, I think we can have more discussion or more research on the coupled fatigue analysis methodology, which I think it will be the kind of research area or most interesting topics that we can have. And to have this, I think also we need to have some theoretical study of this coupled fatigue performance, or also the cable component coupled fatigue performance test to study about how will like copper and insulation layer and the armoring layer performed during the coupled electrical and thermal conditions. So that's my topics and my presentation. Thank you.
Thank you, Mr. Shilu Hao, for your interesting presentation. Any questions? Any questions from Zoom? No? Okay. If there's no question, then we move to the last speaker, which is Mr. Guoyi Li from COOEC. Wei Li, Mr. Li, are you online? Okay, you're online. So
yes,
yeah. Firstly, I would like to introduce you a little bit. Mr. Li is an engineering specialist, currently working in Chinese Offshore Oil Engineering Corporate Limited. He has more than 15 years of working experience in offshore oil and gas industry, particularly in subsea sector. Before joining COOEC, he was working in Annie Wood JDR and gained sufficient experience in mooring and subsea umbilical riser flow line system. He also has project experience in South China Sea, North Sea, West Africa, and also Gulf of Mexico. Okay, Mr. Li, please go ahead. Thank you.
Okay, thank you very much for introducing me. As now it's pretty late in China, so I would like to control my presentation duration as short as possible. 主持人，您能看到我的屏幕吗？
可以的。
Okay. Now I can start. Good afternoon, everyone. Many thanks for Ningbo Orange Cable to offer me this opportunity to share the cable installation experience to everyone today. Although I've not yet get involved in any offshore wind farm cable installation operation, however, I was deeply involved in deep water subsea power cable installation in the past few years. Today, I would like to present the project was just completed in 2020-21, which is the Liuhua 16-2 oil field development project to everyone today. My presentation included 5 parts: project overview, major technical data, cable laying spread, operation go by, and then last section is the testing matrix. The 16-2 oil field is a deep water oil field located in South China Sea, 240 kilometers southeast from Hong Kong. The water depth of the field is around 400 meters. The project scope for this particular cable, scope is to transportation and installation 6 of dynamic power cables. 16-2 oil fields actually including 3 drilling center as shown in the figure below. There are 6 of power cable to 16-2 and 20-2, 3 to each. The length of each power cables varies from 12.7 kilometers to near 24 kilometers. Move to project technical data. The power cable was hanging under FPSO turret with the series accelerators to subsea. The major accelerators including topside assemblies, ballast modules, distribute buoyancy modules, hold down clamp assembly with band stiffener at both sides, hold down structure, hold down clamp and base, cable static section, SPDU, and associated mat structure. The topside assembly including 4 parts: pulling head, diverless band stiffener connector, band stiffener, and the pulling head band restrictor assembly. The total length of the topside assembly is around 21 meters, and the weight of the assembly is around 10 tons. Diverless band stiffener connector assembly was applied for the power cable quickly put in. The assembly includes male and female 2 major parts. The male part can be active by RV through the dual-port hot start as the figure shown below. All 6 of power cable were supplied by Arca Solutions in Mobile, Alabama, US. There are more than 7 on-land carousel are available at Arca Mobile facility. More than 20,000 cable can be stored at the same time in this facility. And this page presents the power cable cross-section design. As all you can see, they are slightly different between the dynamic and the static section. All the cable conductors is 35 mid-voltage conductor. The OD of the power cable ranges from 151 millimeter to 167 millimeter. The weight in water per unit length ranges from 10 kilo per meter to 22 kilo per meter. And the installation MBR for these cables are all around 3.4 to 4.5 meters. There are a large number of ballast modules, and the distributed buoyancy modules were used to form up the lazy X configuration. All these auxiliaries are supplied by Trelleborg Offshore. There are 1 hold back and the hold down structure for each power cable. This structure was designed by Arca Solutions and fabricated and installed by COEC. At the subsea end of power cable, the SPDU, which is the subsea power cable distribution unit, were used for the power distribution. All the SPDU were designed and supplied by Technip FMC. SPDU will be sit on the pre-installed SPDU mud mat. The mud mat is around 17 meters length times 10 meters wide times 5 meters height. The weight of the mud mat is around 50 tons. Because of the very busy fishing operation in South China Sea, hence all the subsea mud mat come with the fishing net prevention hinge. Figure below shows the drilling center layout. All SPDU and power cable were installed outside the circular area. Power flying lead was used to transfer the electricity from power cable to each Christmas tree. In the third section, I would like to introduce the power cable major laying spread. The connector, CSV connector, was used for the power cable transportation and installation. She is a large MSV equipped with the latest DP3, which is a dynamic positioning system. There are 2 subsea cranes on connector. One is 400 ton and the other capacity is 50 ton. Both cranes are fit with active heave compensation and are capable for operation near 3,000 meters water depth. 2 world-class RV are on board. Both RVs can work up to 3,000 meters water depth. There is a semi-auto horizontal laying system, HLS, on the vessel for the cable laying and auxiliaries installation. Major part of the HLS system include a 75-ton 4-track tensioner, openable hang-off platform, and a 2 David crane. Two carousels were used for power cable storage on the vessel. The 6,000-ton carousel is on the deck and the 3,000-ton carousel is under deck. Both carousels are fully rotationable with a loading arm. Other onboard equipment, including transpooling tensioner, which is one is 5 ton and the other is 10 ton, finger crimps, ROV clamp, winches, and so on. In the next section, I would like to go over the operation go by. A table below states the major milestone of the whole project. Connector starts mobilization in Norway on 6 March of 2020 and complete all the cable laying operation by 28th August 2020. It was planned 44 days for the cable laying at offshore, and actual duration of laying operation lasted 39 days. Total vessel days spent on all operation, which including the mobilization, transit, transpooling, cable laying, and vendor standby, is 175 days. Photos below present connector was in Mobile, Alabama for cable transpooling operation, and the cable transpooling was last for 23 days. This photo shows the connector was berthing alongside the finger pier during the transpooling operation. This photo presents a vessel deck layout for the transpooling operation. Cable was transposed from quayside towards vessel stern and then reached carousels. Page 33 and 34 presents the top view of the cable packing in the carousel. Cable major terminations such as the topside, SPDU, and the spice box were packed at the outer area of the carousel. And this figure presents the handling of the major termination on that carousel. And the next pages present the handling of the major terminations at the underdeck carousel. We have performed the detailed AutoFlex simulation to verify and to ensure the rigging setup for the topside and SPDU handling is appropriate. Here are some photos of the spice box handling and the SPDU handling on the vessel. One connector was about to leave US and then transit to China. Unfortunately, the COVID-19 was blown out, and this delays vessel transit schedule significantly. Connector finally arrived in Shenzhen on 7th July 2020, which is about 35 days behind the original schedule. She completed the mobilization for cable laying in Shenzhen, load on more than 20 containers of accessories. There are some difference between the cable transpooling and the laying deck layout. As you can see, the cable travel from carousel and then turning 90 degrees at the vessel mid area, then deploy into water via the HLS at the vessel port site. I would like to present the operation flowchart of the cable laying. After connector complete the mob in Shenzhen, she transited to 16-2 oil field. After completion all necessary preparation work, she then deployed the SPDU, laying the cable static section, then deploy the hold down and hold back clamps, deploy the accessories on dynamic section, and then finally deploy and transport the cable topside assembly to FPSO. After completion of the DP collaboration, pre-lay survey, RE then fly to the pre-installed SPDU mud mat, open the SPDU hinge groove, check the SPDU receptacle, and then get ready for the SPDU deployment. Then deploy the SPDU through the water column with ROV assistance, landing the SPDU on the mud mat with the crane AHC function. We then start laying the cable section with an average speed of 500 meters per hour. Then the mark of positioning for holdback clamp reaches HLS platform. We then stop paying out the cable. Deck crew to install the 2 half type of clamp vertically. Then is the hold on clamp. Connector continue to approach FPSO turret. Deck crew start to install the ballast module and the buoyancy modules. The ballast modules and the buoyancy modules on the HLS work platform. The next step, the crane to lowering the horseshoe type clamp to near hold down clamp position. ROV to connect it to the hold down clamp. Horseshoe clamp will ballast the cable section towards to hold down clamp base. And then the vessel will curve lay the excess cable section to consume the redundancy section of the cable, then lay down the whole back clamp on base. And next, we then land the horseshoe type clamp near the hold down clamp base. ROV connect the tether sling to the hold down base. The final two steps was the topside handling. First of all, the pre-com team will remove the cable monitoring and test kit from topside, and then deck crew to install the pulley head. Connector then use two cranes to upending the topside from originally horizontally to vertically. We then temporarily hang off the topside at the HLS work platform. Recovery the FPSO pulling winch wire to the HLS, and then deck crew to connect the pulling wire to the cable pulling head. Crane then slow lowering the cable topside to the mid-water level, then transfer the cable catenary weight totally to the FPSO pulling wire. FPSO winch continue to pull cable towards to the turret. DBSD male part engage into the female part. Then the cable laying operation is completed. The final section of today's presentation is to give a brief of power cable testing were performed. The CR test was performed during the cable transpooling, and then we perform a full package of the test, which is including the IR insulation resiliency test, CR, the conductor resiliency test, MV, which is the mid voltage cable voltage test, and then the OTDR test. The full test were performed after the cable transpooling. This will ensure there's no quality issue of the cable system when handed over from Aker Solution to the installation contractor. The standard testing equipment, including Mega, ohmmeter, and the OTDR meter. So this is all my presentation today. Thank you very much for your listening.
Thank you very much, Mr. Lee, for sharing this interesting operation experience. Okay, any questions? Due to time constraint, actually, I may miss some questions to the previous speakers. So after this workshop, you may contact the speakers respectively for more detailed discussion. Okay, if there's no more questions, I would like to thanks to all the speakers for your contribution and to all the audience for your attention and for your attention and patience. Then the last session, I would like to hand over back to Professor Moan to give the closing remarks. Prof. Moan, hand over to you.
Thank you very much, Ling. Now we have spent some 4 intensive and interesting hours in exchanging information about power cables, spanning academic research to industrial
Is there any
realities.
voice? I cannot hear anything.
I think here we can hear you. So Prof. Fu, you cannot hear from Professor Moan?
I can hear him.
No, it's okay. No, it's okay. Thank you.
Okay.
Okay. And we have spanned academic research to industrial realities. We also observe, of course, that floating wind turbines are at an early state of development, and also the experience with dynamic power cables is limited. So it was very interesting that we brought in experience from related areas like oil and gas, and also the link between power cables and risers, for instance, and so on. It is crucial to transfer knowledge from related areas. Of course, observe the unique features of the power cables used for wind turbines. I hope you have had a worthwhile experience attending this event. This was the first workshop we organized, and the intention was to give some overview relating to power cables. Some issues were briefly touched upon only. So our intention is therefore also to follow up with other workshops, probably with a wider scope or even more narrow scope, as was touched upon earlier by some speakers. Is a follow-up what Ling Wan said also. If you, in case you have some comments or additional questions, you can contact, of course, the speakers, but you are welcome to contact us also, the organizers, because if you have any suggestions, it would be very nice to get this feedback from you. And our email addresses you find in the workshop flyer. And moreover, as I briefly mentioned, we are interested in this academician workstation to establish cooperation with other organizations outside the key organizations involved in forming this workstation. So if you have some interest, you could express interest in cooperating with us and so on, and we could follow up this also. So let us then end this workshop by thanking the speakers for their good presentations, both contributing to the workshop by comments and questions. Thank you very much. And thank you for your participation.
Thank you.
Thanks to all. I think maybe in addition, I would like to say something, Prof. Mon, because maybe this is a good chance to show our interest to hire more staff in Ningbo University on the wind turbines and as well as riser, power cables, and so on. So if you have any interest in joining us, please contact me or contact Professor Mon. Thank you.
Thank you.
Thank you. Maybe
Thank
you
you,
could take a picture if you want. Yeah. It's will be. Yeah.
Soon, you look very good. So, hello, Soon. I didn't speak to you today.
How do we take the picture? Okay.
If someone wants to.
Yeah, maybe everyone can open your webcam so that we can take a group picture to show the participant of this international workshop. Thank you.
I'm driving now, so sorry.
Be careful.
To go to another location, the new testing facility. Also every day have a visit there to see the progress on the building progress. So you will see that when you visit Trondheim next year, you will see the new construction laboratory.
Right. We're really looking forward to the new facilities.
Okay. The photo has been taken. Thank you. Thank you all.
Okay.
See you next time. Bye bye.
Thank you, and congratulations to this workshop. I think it's quite good. Thank you.
Thank you. Bye bye.
Good luck, everyone.
Bye bye.
Good luck. Good luck.
Bye bye.
Bye bye.
Thank you. Goodbye.